Okay, hi everyone, welcome to SOAP 2024. So I'm Raphael, I'm co-organizing with Cindy, who's right there. So for SOAP this year we have 3 keynote speakers and 8 talks. And the first keynote speaker is Eva Darylova, who's coming from Uppsala University, and she's going to talk to us about recent advances in floating point static analysis. Thank you, Eva.
Thank you for the introduction. Does it work with a mic? If I drop my hand, please just do me the favor and show me that I have to move it up. Okay, so I want to tell you about some of our latest work. So what are we talking about? Most of you will know what finite precision means, but just to make it clear, suppose that we're some kind of embedded engineer and we have some expression that may be, for example, an embedded controller that we need to implement on an actual computer. So the natural choice would be, for example, to use double floating point arithmetic, or maybe if we're concerned about resource consumption, we may choose single precision floating points. Now, at this point, many of you may already cringe a little. So we can just try to test our function, and let's take the double precision one and just use it with some random inputs. And if you do the math a little bit, not that you have to do right now, then this result would be the one that you would expect if you did this computation on paper. If we run this now in the single precision one, then we already get some of the artifacts that many people will expect with floating point numbers. So that result is clearly not quite accurate. But it gets a bit weirder. So if we take the double precision implementation and run it with single precision inputs, we get suddenly a number that is bigger than the result, no, smaller because it's a negative number, than the one that we would expect. We can take now the result, the first result here, and add it 3 times. And then we realize that that original result wasn't actually accurate. The inaccuracy was just hidden by the printing. What we can also do is take our floating point single precision computation and just rearrange the arithmetic a little bit. So on the reals, it's exactly the same thing. But if we now run our test input, we suddenly get the double precision result with single precision floating points. So at this point, if you're an engineer and look at this, you may wonder, well, how do I actually know that my results are good enough? Can I even trust them? So one way, we can always just throw in the towel and just say, well, we'll just have to trust it and just, believe. If this code is, however, running on some safety critical system, for example, on an airplane, then we may want to do better. So what we really want to have are rigorous correctness guarantees. So we can have a guarantee that our computations are good enough, at least for our applications. Now, the quote that I have there from Xavier Leroy is from a talk at Poppel in 2011. So you may ask, are we there yet? Do we have these correctness guarantees? Let me come back to this question at the end of the talk. What I would like to present today is a really quick background on floating point arithmetic and a sort of tutorial by example on today's main techniques for rounding error analysis. And then building on that, I want to discuss 2 of our recent work in pushing this rounding error analysis further. And really, this is work by my 2 PhD students. I was there helping a little bit. Okay, so let me start with the background. And this is mostly so that whatever I say later makes sense. So this is not complete in any way. So I'm assuming that we're talking about floating point numbers governed by the IEEE standard, and they're represented by a mantissa, that's basically the significant bits, and an exponent, that's the range of the number, the size of the number. And typically we talk about single precision, double precision numbers, maybe there is half precision these days as well. At least single and double precision floating points are typically supported by hardware, so that's what you will have on most computers. What we care about for arithmetic operations is that the standard specifies that these are computed as if we had real numbers and then rounded. So the rounding can be different. I will be assuming rounding to nearest, which is basically the default for most programming languages. Based on the definition of how arithmetic operations are rounded, we can use an abstraction that basically says this, that a floating point result is as if so a floating point number is as if we had it in real values, so that's without the tilde, with two different kinds of errors, where one error is for normal floating point numbers, that are the normal ones, and the d is for d-normal numbers that are very, very small. And then basically for different precisions, we have different values of the bound on these two errors, so the epsilon and the delta. The larger the precision, the smaller the error bound will be. There are also special values for floating points, like not a number infinity, but I'll mostly ignore these for this talk. One consequence of rounding is that floating point arithmetic is not associative or distributive, so the usual rules that you would expect on real numbers do not hold. So the results will not be the same because the rounding errors in both cases may be different. And then there are some additional identities, like we cannot dividing by 10 is not the same as multiplying by 0.1, and similarly here. What this means for our analysis, that we need to follow exactly the order of computation as is written as is basically written and will be executed, because if the order is different, the errors may be different. All right, so now we know about little bit about floating points. How can we bound rounding errors? So how can we compute automatically a guaranteed upper bound on these errors? And I'll be using this very simple expression through most or half of the talk. So we have a function with two inputs, and we just square them and add them. And importantly, we have bounds on both y and z. So these bounds are important because if these values would be unbounded, the error would be in general unbounded as well. So when we talk about rounding errors, it only makes sense if we talk about input bounds in most cases. So and then what I assume that we have this real valued specification, and then what we want to have is actually an implementation in floating points. So all inputs and all operations are floating point valued. And we may have some kind of input errors. And the goal is then to compute the difference between these two expressions, assuming that y and z are in the bounds as specified. Now, we have to compute an over-approximation. It is, especially for double precision, it's impossible to get the exact errors, so we can't just enumerate all of them. And the main challenge now is to compute accurate bounds. I can always give you a guaranteed error bound of infinity. It's going to be sound and correct, but completely useless. So basically the challenge is how close can we get to the true errors while still being guaranteed over-approximation. Now the expression as given here is too complex to reason about manually, automatically, at least today, because it combines real valued and floating point reasoning. So for example, we cannot simply phrase this as an SMT query. Well, I mean, we can, but the solver will not really give us any result. I'm talking here about absolute rounding errors. You may also ask, so what about relative errors? Let's stick to this because that's even harder. The relative errors are even harder. All right, so this is the thing that we're after, and it's complicated because it combines reals and floating points. So what we're going to do is use that abstraction from before and apply it to our expression. So if I take that f tilde, I'll make it now into an f hat, where all of the floating point variables and operations are replaced by this one. And I'm introducing new errors for each of them. So this is now very complex, but it is now only real valued. So there's no more mixing between floats and real theories, so it's only reals. But this is still too complex to reason about automatically for anything but very small expressions like this one. So what we need to do is basically find some ways of abstracting over this. And there's today more or less, and I'm generalizing a little bit here, two approaches to rounding error analysis. One is data flow based and one is optimization based. So the data flow based will use data flow analysis with interval-like abstract domains. So just to illustrate with an example, if we represent our example as an abstract syntax tree, we will track ranges of all of the variables because the errors depend on the ranges, and we will propagate them through the tree. And then we will similarly track the errors at every node, starting from the inputs, and then propagate them upwards through the tree. Now here I'm not telling you exactly how this propagation works, so this is governed by transfer functions that at this point are fairly well understood. So if we just have an addition, just to give you an idea, the errors get added. If you have a multiplication, it's a little bit more complicated. And basically the trick in this approach is to have abstract domains that are good enough so that you don't lose too many correlations between variables and error bounds remain accurate. The second approach is to take the definition of the absolute error and look at it as an optimization problem. What it is, where we're maximizing the difference, so that's an optimization problem. But it is too complex to solve as is. So what we need to do is simplify it a little bit further. And I'll tell you a little bit later how to do that, or one way to do this. And once we have done a little bit more simplification, then we can throw an optimization tool at it and actually compute a bound for the error. Any questions so far? Okay. So there's tools that exist today that implement one or mostly one of these approaches, and you can use them on some code. Typically, the data flow-based ones will be a bit faster, and typically the optimization-based one will give you tighter error bounds. It's not a hard cut, but that's the typical case. So there's no free lunch, if you will. The problem with both of these is that they're non-modular. So if you have a bigger piece of code with, for example, several function calls that are called several times, you will have to inline them and the whole thing will probably blow up in your face. They're also not particularly good at supporting loops beyond, again, unrolling and looking at straight line code. So, and that's the setup that we started off. So I want to now talk about our project about doing a modular analysis. And then after that, I'll talk a little bit about how we can do something about programs with loops. All right, so the first approach starts off from the optimization-based technique. And what I haven't told you yet is how do we do that first step so that we can actually use these optimization tools? Now, there's going to be a little bit of math. If you don't follow all of that math, that's fine. And I'll try to point out the really important parts of this math. So what we're going to do this simplification with is a Taylor approximation, which is a standard technique in math and physics to simplify complicated equations. So a first-order Taylor approximation of a function f, so that's our function f, looks as follows. So we evaluate f at a point that we choose. So we typically want to choose a point that works really well for our application. Then we take a first-order derivative with respect to some variables that we choose as well. And then we have a remainder that bounds the error. So basically we approximate f by a sum of terms. And by having this remainder, we then have a bound on how different this approximation is from the true function. Now, I'm talking here just about the first-order Taylor approximation. In physics, you may see several second order, third order, and so on. For our purpose, this is enough. So what we're going to do is we will compute a Taylor approximation of our f hat around the point yz 0, 0. So this is our suitably chosen point, which means that we choose a point where the variables e and d are all 0. So that means that's the point where we have no error. So that's this one here. And then we have a bunch of terms. So this is the Taylor approximation for the running example. Now this looks really complicated, but it really helps us because each term itself is simpler. And we can look at each term separately. So this is how we get the simplification. Each term will be simpler because we're taking the derivative with respect to our error variables, and they will typically not occur in the whole expression, but only in smaller parts. So in each term, much of that original expression will disappear. And that f hat of our suitably chosen point happens to be exactly the real valued function. So that means that when we plug this into our error expression at the bottom, this part and this part, at the beginning there will be the same. So we only end up with the derivative terms and that remainder. So the important thing is we're doing derivatives, and by doing so we get many terms, but each of the terms is simpler. So and once we have that, then we can apply our optimization technique. So just to summarize, what we're doing with our original error expression, we compute a floating point abstraction based on the IEEE standard. Then we use the Taylor approximation, computing derivatives symbolically. And then we can bound the individual terms using some interval domain. So we can either use standard interval arithmetic, or we can use more advanced techniques like branch and bound. Now this approach, and this is originally from the tool FP Taylor, this supports arithmetic and transcendental functions like sine and cosine. So we can easily do sine and cosine because for these we have derivatives that are well defined. So we have an abstraction step and we have an optimization step. Now this approach as is does not support function calls. So if you have function calls in your program, you have to inline them all. So, and this is what we want to avoid. So this is now our extension of this approach. So we start off, and I'm going to go through this with an example. So this is our running example. And now we will abstract the power function with a function call. Now, this is a very simple example for the sake of the talk. Typically, this one you would inline, but just for the sake of presentation. All right, so you will notice that the input range for our function g is large enough so it's safe to call g with both y and z so that we don't have to inline the full function. So once we have computed these error specs, then in the second step we will instantiate them with the appropriate context and actually compute the error bounds. The goal is to abstract enough, but not too much. So what does this mean? So we can abstract, so we can basically compute these specs as a constant error bound, but this will lose too much accuracy because notice, for example, in our, and I'm too short to point there. So when we call g with y, then y is much smaller than the full range of g. So the error that we compute if we just compute a constant bound for g will be much larger than what we actually get when we call g only with y. So we don't want to just have a constant. We want it to depend on the inputs somehow, a little bit at least. We can go to the other extreme and just pre-compute all of the derivatives and don't do any actual computation, but this will give us modest performance. This will just amount to essentially caching, a smart caching. So what we want is something in between. We want to pre-compute some parts that are suitable to be pre-computed, but not too much. All right, so how do we compute these error specs? We follow the rounding model and extend it with procedures. So basically we treat function calls or procedure calls as if there were an arithmetic operation that has an error attached. So if we take our example, then the g is the same as we had before with just the e's and d's. And now for the function called g, we express it as the real valued result of g, of the function, plus some error. And the error is exactly that error specification that we want. And this error specification depends on the input parameter. So it won't be just a constant, but it will be a function of the inputs. So the values of these symbolic variables are only needed at instantiation time in the second step. All right, so how do we... So once we have this abstraction, we will proceed as before with the Taylor approximation. So we will compute the derivatives with respect to the error variables, but now we will also compute the derivatives with respect to the error variables associated with the function calls. They're errors as well, so we do the same thing there as well, and we treat them symbolically here. And then, here comes the abstraction part. We realize that some of these terms are actually typically very small, because, for example, the errors due to d-normal numbers are typically small as well. So we pre-compute them at this point using the full range, which does a bit of an over-approximation, but it's typically fairly small. So the part of the derivatives remain symbolic, and part of them we pre-compute at this point. And then, once we get to the second step, we instantiate all of the error terms with interval analysis. So we just plug in the values, the bounds that we know for the E's and the D's and so on. And now when we compute for the betas, then we use the actual intervals of the input variables of Y and Z. Now at this step we also check that we're not using a function whose range is smaller than the inputs, so that's a quick check. And the trade-off that we do here is that parts of these betas are computed with wider ranges than what is actually happening at the call site. But we do this computation only once. So we don't have a formal proof of the correctness, but we have a correctness argument that if you inline these error specifications without the pre-computation, then we get the same error expression as you would get with the regular inlining approach. So, a little bit of evaluation. There were no existing benchmarks for this, so we made a sum up with some matrix computation and some complex numbers. So we have a bunch of procedure calls. So obviously this approach is only useful if you have many procedure calls, because otherwise there's too much overhead of computing the error specs. Okay, that's the copy table from the paper, but let me give you the highlights. So Hugo, that's the name of the tool in the paper, just to make it different. So it is implemented within the DAISY framework. So that's the approach that I just talked about. Now, it's typically, if you have many function calls, the analysis will take significantly less time than DAISY's approach or the FP-Taylor approach in the FP-Taylor tool itself. So both DAISY and FP-Taylor have to inline the function calls. And then for some larger benchmarks, FP-Taylor times out after an hour. What we also get if, well, compared now to the error bounds with DAISY, they're actually, so if you compare these two numbers, they're much tighter than DAISY's error bounds, even though the analysis takes half the time, and this is because this approach uses the more accurate optimization-based approach and not the data flow analysis one. But we have made it scale up to actually work for these kind of programs. So that's the very short summary. Any questions? Okay, the remainder of the talk will have less math, promise. Yes. Yeah.
Are there like known error bounds, like theoretical worst case error bounds that you should be reaching here? Do we know how close the results that Hugo produces are to that?
Yes. So I do not have them Okay, there's two answers to this. So we can get an upper bound on the errors by doing testing. Okay. So just running the programs with many, many inputs.
Okay.
And this we would have to do on the inline function calls. I don't think we have done it for this one. Typically, these error bounds are within 1 or 2 orders of magnitude.
Okay.
But I'm just talking about my previous experience. We haven't actually done it here.
Thank you.
Have you looked at more complex call chains? So imagine not only f is calling g, but let's say f is calling g, is calling h, and so on. And for every function, you have more than one call site. So, for example, j might be called at with a very tight range and with a very wide range another position. Plus, you cannot just pre-compute it once because g might also be called by, let's say, f, which is called by a, and so on. Have you looked at these complex cases, and then what influence does this have on the parts that you do pre-compute? You said they are very small, but what happens if you kind of have so many call sites, some of them with larger boundaries? Shouldn't this add up then?
So as long as your call chains are don't have loops, this will work. But this will mean that, so if your ranges vary a lot, then the approach will naturally always assume for the pre-computation the largest range. So you will get some over-approximation by this.
So there is no concept of saying, okay, if this is called more than, I don't know, 10 times, or with ranges that differ too much, then let's just not pre-compute it, because probably I'm losing too much precision, even if it may give me some additional performance.
Yeah, so we don't do this automatically. You could do it manually by basically having copies of the function. I guess that would be a sort of natural next step to do this. It wouldn't change anything in the approach, so that would be more, I guess, implementation and a bit of figuring out when do you split. You can mimic it manually by having copies of the function with different ranges.
It would be non-trivial to find out when to pre-compute and when not to pre-compute. Imagine you have like the full implementation of some flight controller. This can be a lot of code, and then you don't want to do this manually.
Yeah, no, so we don't know how to do that automatically.
Okay.
Hello. Just a general question about the input specifications. So I was wondering, like how much domain expertise you need to find like which inputs make sense.
Good question. Right now, we assume that the user will know. I mean, typically you would expect. So if this is an embedded system, then this would be the sensor inputs or something like this. And for that, I would assume the ranges are known. You would know what the specification of your sensor is. But we assume that the user knows.
And just one quick follow-up question. Could you also apply these to other kind of mathematical software, like, you know, like general math functions or something like that?
So if you talk about something like library functions, like elementary functions, then I don't think this is the right approach. Just because the error bounds will not be good enough in that case. Also, for a library function, you have, I guess, more time to spend because you will do this once and then the function will be used in so many more contexts. So the techniques for these error bounds for sine, cosine, and so on, they're very different. Okay. So that's not the right approach.
Okay, thank you.
So I wonder where these benchmarks come from, or in general, what would be a good source of real-world benchmarks for this kind of work?
I wish someone could tell me. For now, basically everyone in the community is just making them up in some way, or you know, we pick them from. Some of these benchmarks come from embedded systems papers. There were actual proposed controllers. Some of these for the complex. The name tells you a little bit, so it computes an instant current. So they come from some codes that we found online from a physics application. But there is no standard benchmark set right now. I mean, there is one, but that does not have function calls. All right. Then let me continue with the second part. So I said a few slides back that we don't know how to do this analysis modularly, and the analyses are not particularly good about loops. So what about loops? They're tricky in general. So if we just take a very, very simple piece of code, programming language syntax doesn't matter. And I'm plotting here the actual errors with double precision. Then you will see that typically these errors will grow with every loop iteration, but this growth is not necessarily monotonic. So it's complex, that's my main point. In program verification, you would be looking for loop invariants, typically, to handle loops. But today we only know how to compute these for very special kinds of loops. So this is hard with floating points as well, mostly because of the complexity and because these errors tend to grow. So there's no simple upper bound you can find. But even if you just look at finite loops, then these are tricky because then we need to unroll them, and this unrolling scales poorly. So what we need is, or what we want, is effective abstractions. Again, there is two sides to this. We can always compute a trivial error bound of -infinity to infinity, but this will lose too much accuracy. Or we can do the naive unrolling, so we just unroll all of the loops, but this will have modest performance. So we're again looking at something in between. And we're going to look at very specific kinds of programs with loops, and I'm going to illustrate what we want to do with an example. So we have a timeline, we have a bunch of time steps, and what we're computing or simulating is a heat distribution. So initially we have an array, think of it as an array with values of temperatures of a rod or something like this. And then we want to compute the temperature after several time steps of the middle element. And the way this simulation works is we look at a sliding window of always 3 elements, and from these 3 we compute the temperature of the middle element at the next time step. And we basically do these for all, so we do the sliding window, and then in every step our array gets a little bit shorter that we look at, and then we continue in the next time step, and so on. Exactly what this application does is not so important. It's just that you have a little bit of idea of the computation that we're doing. So there is some kind of loop because we're doing this for several time steps. And there is another kind of loop because we're going through this, this array. So we can implement this computation, for example, in C. So this is syntax that we can run through the tool Fluctuat to actually compute an error bound using unrolling. So this will be naturally implemented with 2 for loops. Again, the exact details don't really matter. The point is there's 2 loops, and they're finite. We can unroll this completely and then run it through the tool Satire to get an error bound. But this will be 1021 lines of code. So that will take a while to analyze, even though the individual operations are relatively simple. So what we are proposing, what we are saying is, well, first of all, it's nicer to write this in a functional style. So this is the same computation written with, so this is a little bit syntactic sugar for the sliding window. This is a sum of elements, so this would be in functional style a fold. So we're writing this now in 6 lines of code, and we have no explicit indices, so we don't have a for loop that explicitly indexes into the arrays. So the vector data type there, think of it as an array, basically. So we are saying we should write this kind of code in this kind of functional style, and this also makes it easier to analyze the rounding errors, or at least it makes it faster. So we want to express these loops over data structures. So now I'm just talking about code that has some kind of vectors or matrices, and we want to use functional iterators. And then we will define an abstraction over the data structure elements, and I'll explain in a second what this means. But the whole goal of this abstraction is to avoid duplicate analysis. So for example, if we look at this, the computation, so that's the one that is done in each of these sliding windows, this is basically the same. And if our elements have the same range, then if we do unrolling, we're repeating duplicate computations. And this is the one that we want to avoid. the whole idea of using this kind of high-level language to express the code is to make it easier for our analysis to figure out exactly where this duplication happens. If we just have a simple for loop or completely unrolled code, we would have to reverse engineer this information. But here we get it right from the code. I'll have more examples of this later. So just to give you an idea what we get from this, so this particular example we can analyze in much shorter time than the other two tools. At the same time, we don't get the tightest error bound. So that's the cost for the abstraction. We can do the analysis faster, we will compute slightly looser error bounds. All right, so the whole approach is implemented within DAISY, but it's called DS2L, so that's also the branch where you will find the implementation. And it basically consists of this functional DSL over data structures, an abstraction of these data structures, and then transfer function so that we can use, this time, the data flow rounding error analysis. And let me just give you a very quick overview. So the functional DSL that we propose, though the point is really just to demonstrate that the information we get from this DSL is useful. So we have real valued vectors or matrices. There's no matrix in this one. And then the input specifications will provide a maximum size of the data structure. So this is interpreted as the maximum number of elements. And we provide ranges for each element. We can also provide some sub-ranges where the elements have different values. And then there are some operations that we currently support, and this is basically, we looked at a bunch of applications that we found online and made the DSL work for these. So we can use the regular higher order functions, map, filter, and fold, and the sum here is just a fold with some syntactic sugar on top. We have some element-wise operations, so these are two vectors that get multiplied element-wise. We have a few domain-specific functions that can be expressed as maps and zips and so on, but they're nicer to write like this. And then we have a few non-numerical operations, so we can get the length of an array so that we can actually have a loop. So the second loop here is expressed as a recursive function, but that one will be unrolled implicitly. All right, so then just to give you a quick idea of the abstraction that we want to have. So suppose that we have a vector v, and we're mapping over it and adding 3.5 to every element, and then we get the result stored in an array R. So, and now suppose that some of these elements have 0 to 1 range, and the others are 2.5 to 4. So when we do, so this means that we can have only two different results of adding 3.5. If we unroll, we have to do this computation 8, 10 times. But really what we really only need to do is to do this computation twice. We only need to look at one of these green elements and one of the orange or yellow elements. Similarly for the error analysis, we only have to compute the errors once for the green and once for the orange ones. And that's basically what we're doing. So our abstraction will group these data structure elements by their range and then do the error analysis only once for each of these ranges. These ranges don't need to be consecutive, so we just look at the indices in there. And then the actual error computation is reduced to a straight line data flow analysis. So we reuse the existing approach, the second one from that overview slide. But the point is that we use the semantic information from the input DSL to figure out how often do we really need to do this error analysis and only do it once. And then the data flow analysis we just do with simple interval arithmetic. All right, so in the end we get our expected result. So this was just for the ranges, and then similarly we do that for the errors. Now this is obviously hiding a lot of details here, but this is the core idea. Now we again had to make up some of the benchmarks. So these were found online by my student, Anastasia. And we tried to make them diverse in the sense to cover several different applications. But I have no claim that this is exhaustive in any way. So our main goal was scalability. So if you look at large benchmarks where basically the loops are, the data structures are big, so we have to do large loops with many iterations up to 708K, then our approach basically handles many more of these benchmarks. So we can handle 67%, whereas the other two tools can do less than a fourth of these. So if the other two tools do compute the result, then our approach is also several x faster. Again, there's no free lunch, so our errors are a bit more loose. So compared to Fluctuat's, ours are about twice as big. They're comparable to Satire's approach. So are we there yet? I would say that if we have just pure arithmetic, straight line, no loops, no conditionals, and so on, probably yes. So there's tools that can do that, and the list is not exhaustive. Are we there in terms of scalability? Maybe, maybe not. Are we there? So I've completely hidden any discussion about conditional statements. That's because they're tricky. So if we have a conditional statement like this, so we have some arithmetic computation, and then we compare the result against some kind of threshold. Now the problem here is that our real valued execution may now take a different branch than the floating point implementation will. So we get an error, an additional error due to basically divergence of control flow. Now if the code is simple as this, we can handle it already today, but anything more complex, I don't think we really know how to do that. And then the loops, I'm leaving that box open as well. So we can handle some kind of loops, so there's different approaches for different kind of loops. But for general loops, say for a simulation of the Jupiter orbiting the sun or something like this, I don't think we can really do much yet. But I think we can do better than the garbage times garbage approach. And that's what I wanted to say. Thank you.
Thank you very much, Eva. One more question.
Very interesting. Can we make some sort of constructive approach out of that? Like rewrite the code, simulate again, but not in a like shotgun approach. I just change something and see whether my bound gets tighter. But from the bounds analysis, get an idea of what to change to make it tighter, and then hopefully have some sort of iteration that gradually gets us to as close to the real numbers as we could get. Because I think that could be very fascinating, especially then when you also look at the, for example, time and memory requirements. If you're talking about constrained microcontrollers like flight operation controllers, I mean, these are usually not x64 chips with all the memory in the world. But if you have an approach where you say, okay, these are my hardware bounds, and now let's get the best out of it, that would be awesome.
So if you have resource bounds, so if you have limited resources, you probably do not want to get close to the reals, but you want to reduce your precision as much as possible so that your results still remain accurate. So then you probably don't want to use double floating point precision, but you want to use 16-bit fixed points or something like this.
Yeah, my idea was more like you can compute the error bounds, but you have already shown that even if I just change the formula slightly in the code, this can make a difference. So if I say, I know that I can't just bump up the precision, I can't just go to double precision, could your approach be used to say, hey, this is code, please do optimize it. I have to stay with single point precision, but please rewrite my code in such a way that I'm getting the most out of it.
So some of this our tool does already. So if you have straight line, we have an optimization tool, optimization approach, and there are other tools that implement this as well that do this kind of rewriting. There is, as far as I know, no analytical solution for this. So the problem is NP-hard. So it's all heuristics. So we basically try different rewritings and rerun our analysis and try to find the one with the smallest error bound. But this is an heuristic search. So if you have a short straight line code, this can be done already. That said, typically the improvements will not be huge unless you have a cancellation error, so a really bad way of writing your codes. We can discuss offline a little bit more. But if you don't have this kind of cancellation, then typically what we have seen are improvements of 50% of the error bounds, so maybe not even an order of magnitude. So there's not that much. So you can do a little bit, but not that much.
Thanks. I really like this idea about the specification for the loops. But you had shown that you have two different bounds. Sorry. Do you assume equal distribution about those two?
Equal distribution of what? Sorry.
That they both happen equally often, because it seems like in the example you had half of them with the one distribution, half of them for the other distribution.
That was just by chance. So you can, in the specification of the bounds for the data structure elements, you can either say they all have the same range, or you can specify every individually, or anything in between.
Ah, okay. And this specification, I assume this is not pretty easy for people to write. Do you think there's one way to automatically infer this from the code?
I guess this is a similar question than Cindy had. So this kind of static analysis will basically work on relatively short pieces, even if you can do some procedure calls. So we had some previous work where we looked at even larger pieces of code, say 2,000 lines of code. And then this whole arithmetic operations, they'll be hidden somewhere in some function deep in the call stack. And it's only that one that we really want to analyze. But we do need these ranges. So there we use the dynamic analysis to help us find an under approximation of these ranges. I'm not aware of a static analysis that actually worked.
No, I think I was referring not to the ranges, but to the specification. It seems to me the specification needs to be written by hand.
Yes, exactly. But for that specification, you need the ranges of the inputs.
Yeah, but the functional style, is that possible to infer somehow from the imperative program?
That doesn't change the fact that you have to specify the ranges. But
Sure
maybe
it
I'm
does.
misunderstanding
Yeah, sure. That's two different problems.
Yeah.
Okay.
One last question.
Hi, kind of an outsider's question, but so I see that you compute, tighter or looser error bounds. At some point at a higher level, this has to relate to some kind of assertion that you can either prove or not prove, right? Like some correctness property about the software. I don't know if there are, maybe this relates to the benchmark questions. It seems like that's the bottom line question, right? Not necessarily whether you can prove the tightest possible error bound, but whether it's good enough to prove your correctness property. Can you give some intuition on the connection and whether these error bounds are almost good enough, or no, we need to do way better to prove the assertions that we care about?
Yeah, I probably can't give you a very good answer because it will depend on the application. So for example, if you're looking at an embedded controller, then the error bounds that you can compute, or the rounding errors, will influence the stability of the controller. If your errors are smaller, there will be a larger range where the controller will be stable. Now, what is good enough will depend on, for example, the proof of stability of your controller. Out of that, you typically assume some kind of noise term that will tell you, the thing is going to be safe as long as, your error is not bigger than this. And then that depends. So I don't think we can say that, if we're on the order of 10 to the 12, then it's good enough. It really depends on the application.
Okay, let's thank Eva again. And the next talk is by Irina Dudina, from the University of Edinburgh. Unfortunately, she couldn't come in person, so this is going to be a pre-recorded talk with then questions. And we hope it will work.
Hello.
Fine.
Okay, great. Can you hear us, Irina? Great. And okay, so I'm going to start sharing your recording. And okay. Oh. Remote talk. Okay, and you can talk to Irina through this.
Okay, and this is a talk by Irina about static analysis for transitioning to Cherry. And let's start.
Hi, my name is Irina Dudina, and today I'm going to talk about static analysis for transitioning to Cherry C++. So let's talk about Cherry first. Cherry stands for Capability Hardware Enhanced RISC Instructions. It extends conventional hardware architectures with architectural capabilities. It enables fine-grained spatial and temporal memory safety and scalable software compartmentalization. It reuses conventional software stacks based on virtual memory and C++ and supports smooth incremental software transition within existing ecosystems. It provides extensions to MIPS, RISC-V, and ARM have developed a processor prototype and evaluation board called Morello. So let's look at Cherry protection. Let's say we have a simple C program. Here in function main, we have a local array of 3 elements, an additional local variable secret, and we pass an address of this array and its size to a function foo that is supposed to print all the elements of this array. However, there is a bug in the implementation of function foo. We should be having strict comparison here instead. So we'll be having an off by 1 error in function foo and printing 1 extra element. So if we look at the memory layout of the sec frame of function main, we'll see 8-byte pointer, then 3 integers of an array, and then 1 extra integer secret. And if we print 4 elements starting from the first element of the array, we will have our secret leaked. Now let's take the same C program without any modifications and just recompile it to Cherry and run on Cherry architecture. So first thing we'll notice is that our pointer now is 16 bytes long and is implemented as a capability. It means that in addition to an address value that points to the start of the array, we also have bounds, so a range of memory addresses of the object that this capability points to, and permissions for the memory access. So now every time when we are using this capability to access memory, hardware will check whether this memory access complies with bounds and permissions of this capability. This is true for the first 3 iterations, but on the last iteration of the array, we will have an out-of-bounds access. So this will result in hardware trap. Therefore, Cherry will protect this vulnerability in function foo from being exploited. Now let's take a closer look at Cherry capability. Here we have a typical 128-bit representation. It contains 64-bit address, bounds in a compressed form, permissions, and other metadata. Also, every capability on register or in memory is supplied with out-of-band software inaccessible validity tag. So any attempt to tamper with the representation of this capability, for example, manually changing bytes that represent permissions, will result in clearing this validity tag and this capability becoming unusable. As we've seen in our example, all dereferenceable pointers and implied virtual addresses like return address or PLT entry are implemented as capabilities in Cherry. And this is seamlessly supported by compiler, language runtime, and operation system. So one of the key benefits of Cherry is that you can take C++ source code and with minimal modifications, recompile it to Cherry and immediately benefit from the memory safety that Cherry offers. So the amount of changes that you need to make in terms of lines of code is reported to be very small. It varies from 1 or few % for low-level system pointer-heavy code, and it's a few orders of magnitude less from it for a general-purpose code. Additionally, many compatibility issues are detected and well explained by the compiler during compilation. However, there are certain issues that are not detected by the compiler and only uncovered during runtime. So it would be really nice to have a static analysis tool that can uncover more compatibility issues statically. So although our whole Cherry project is about memory safety, I just want to emphasize that in our static analysis tool, we will not be looking for out-of-bounds memory access or another vulnerability. We will be looking at portability issues, so patterns of code that work fine on the architectures it was originally written for, but will not work on Cherry. One landmark example of such transition from one architecture to another would be a transition from 32-bit architectures to 64-bit. So we more or less know what kind of problems arise during that kind of transition. And impact of Cherry on C++ programming model is well studied and discussed in these papers. So main things are increased pointer size and alignment, which often breaks legacy code assumptions. Pointer provenance means that we cannot modify parts of a capability or copy a capability not as a whole, because that will lose the tag. Also, Cherry affects pointer representation, which has an impact of the semantics of the pointer equality, and affects certain programming patterns like using bitwise arithmetic to align pointers, for example, or storing metadata in the unused bits in pointer representation. So we developed our static analysis tool in the Clang Static Analyzer framework, which is part of Clang compiler, and we used a downstream version of Clang that has Cherry support. Clang Static Analyzer is extensible with custom checkers, and it provides 2 levels of analysis: past-sensitive interprocedural checks via symbolic execution, and simple syntax-level checks via AST matches. So let's talk about just few checkers that we have implemented. The first one is about pointer alignment. So any unaligned memory accesses in C is UB on any architecture. An unaligned access can result in a fault, affect atomicity or performance. However, these alignment issues may not manifest in real world due to certain several reasons, like ABI guarantees or fragile properties of a current data layout, or just choices made by a compiler. But when moving to another architectures, all these properties may break and the code will become not portable. Even if the pointer access is really unaligned in runtime, the ill effects on certain platforms like x86, for example, can be so subtle that no one will notice or no one will care about these issues. However, on Cherry, these issues, alignment issues, become more pronounced. First of all, because the alignment of capabilities are so big that it easily breaks legacy code assumptions. Also, unaligned loads or stores of capabilities always generate a runtime hardware exception. That's because these validity tags are only exist for capability aligned 16-byte aligned memory locations. Additionally, if you're trying to memcopy a capability through an unaligned memory, for example, temporarily memcopy to unaligned address and then copy it back to the aligned address, this will result in memcopy function splitting the capability in two parts when copying it, and therefore that will clear the tag in the copy. And even if you then copy the capability back to the aligned, properly aligned address, you will not have the tag back. So your capability will be invalid, and you will only notice it when you will try to reference it. So this issue will be hard to investigate. So in order to detect this, we created a symbolic execution checker that reports casting of underlined pointer values to capability aligned pointer types. Also, it reports storing not properly aligned pointers to capability pointers and an attempt to copy a capability through an underlined memory. In order to report this, we track pointer and integer alignment, relying on type restriction, pointer and integer arithmetic, and aligning attributes. And we also track memory regions that may contain capabilities. So let's take a look at the example of one of the warnings. So here we have a pointer to the structure that contains capabilities. Therefore, this pointer must be, the value of this pointer must always be capability aligned. And this is passed for an initialization to this function. And this function assigns an address of a flexible array field to this pointer. And this flexible array field is not properly aligned. So this allocated memory will be unaligned, and the structure stored there will have unaligned capabilities. So these capabilities will not be valid or will lead to hardware traps. So in this case, we are kind of lucky that we actually have the call to the function that asks to allocate memory for capability aligned object. But this kind of functions are often implemented in the library, and also due to the limitation of an interprocedural analysis, we may not have this call reachable. So we want to still be able to detect this kind of unaligned memory allocation. So in this case, we can argue that this pointer to void, we don't know the type of values that are supposed to be stored there. So we can argue that this might be designed to store capabilities there. So this memory should be capability aligned. This is the heuristic we use. Any external pointer to void, external means global variable, structure field, or function parameter of top level function in the analyzed call stack. So any pointer to void can potentially be a pointer to capability, and all allocated or assigned memory should be capability aligned. So we'll discuss the implication of this heuristics later. So another checker is capability copy checker. It detects custom implementation of copy routines that perform a piecemeal copy that will, during copying, break capabilities in several chunks, like in chunks of this size of long, like in this example. So the problem is that the resulting capability, if we were copying capabilities here, the resulting capabilities will not have the validity tag set because we didn't copy it as a whole. So this is implemented as another symbolic execution checker. And again, we are using this heuristic about void star assumption because this is a library function. We may never see an actual call of memcopy with an attempt to copy capabilities with it. So we have two more checkers. One is working with capabilities to integer conversion. So here we have, this is also a symbolic execution checker. Here we have conversion from pointer to not capability type. Pointer diff-t is just an integer type in Cherry. Therefore, we will lose provenance here, and resulting aligned capability, aligned value will not be a valid capability. So another example is Cherry compatible pointer arithmetic. For example, here we're trying to perform a branchless select on pointer values. So we're XORing two pointer values, but on Cherry, capability can only be derived from a single other capability. So we cannot choose here which side to derive a capability from. Either would be wrong. So this code will need to be rewritten, and this checker detects such cases. And the last checker just detects conditionals where we check pointer sizes and fail to consider 128-bit pointer sizes. This is a very simple ISD checker. So we evaluated our static analysis on the selection of a Cherry BSD ports. So Cherry BSD is a FreeBSD with Cherry support, and it has its own ports tree. So the total amount of analyzed code was 2.5 million. We found that the most useful warning is useful checker is the one that provides alignment warnings. So we could see that warnings that rely on this void star assumption have significantly lower true positive rate. But we do not want to abandon this assumption because therefore we will lose some very good true positives that are hard to detect and investigate otherwise. So same applies to the second checker, tag stripping copy of a capability. Again, such low true positive rate is explained by this assumption, but we actually detected a custom implementation of memcopy and qsort and other tag stripping functions. So the pointer to integer checker has higher true positive rate here, but these warnings are mostly intentional code, so this won't be fixed. So we don't find this checker very useful for this particular selection of packages, but we've seen other good examples of warnings for this checker in other projects. And the last checker has only one warning, and that was true positive. So as a result, we added Cherry support to Clang Static Analyzer, implemented 4 Cherry-specific checkers. We had to adapt build interception tool scanbuild to Cherry BSD to be able to perform analysis on Umbrella. We evaluated our static analysis on a subset of Cherry BSD ports and reported a few fixes, some of them already accepted. And there's more to be done in this direction. We could use static analysis to provide suggestion for the code patterns that could be slightly changed to benefit even more from Cherry protection. So this is marked as future work here, but this is actually has been already done after we submitted our paper. So this is it from me today. This talk was delivered to you from a Cherry BSD running on an ARM Cherry platform. Thank you for your time.
So thank you, Irina, for the talk. And hopefully you'll be able to answer questions. Are there questions in the audience? And where are we on the... So can you hear us, Irina? Yeah. Okay. So that's first good point. Are there questions? Okay, one there.
Hi. Have these issues been reported back to the original authors of the tools? And you know, even if they don't have Cherry hardware, were they interested in fixing them? Are they like generally more in, you know, particularly the alignment issues? Are they like, oh wow, that's great? You know, what was the sort of user response?
Yeah, so that's a very good point. Actually, alignment checker reports
No, they're still doing stuff.
capabilities for any types. So usually and open source tools. So none of the fixes we found with our static analysis, I think, were upstreamed to the very upstream yet, but definitely we are developing those in the sense that they should be upstream, and other Cherry compatibility issues are definitely accepted by the
And there's coffee break until 10:40.
Hello. Okay. Hi, everybody. I'm Max. I'm presenting, now that we've been thoroughly scared of static analysis of dynamic languages, we're going to do a little bit of work into how you don't do static analysis of Python. It's a project I did with CF, who's here as well. It's called Doctor We Notice because we have information about the type signatures we notice. This is an SNL character. So we're going to talk about the state of Python and the C extensions that are commonly used. We're going to talk about why this bites in PyPy, a fast Python runtime. We're going to talk about how we made it faster in PyPy, and then how this sort of affects the broader dynamic languages ecosystem. So Python is a very widely used language. It's got a bunch of applications, mostly to glue C libraries together. So that's the CPython logo. NumPy is a big library for math. It's widely used in Python. Blender is a big C application that embeds Python. And Qt is a GUI framework that has Python bindings, so you can build C++. You can use in C++, but you can also bind from Python. Because CPython was not designed for performance, the call for performance came, and the developer's answer was, oh, just write a C extension for the hotspot of your program. So that means over the course of 30 years, you get a bunch of C extensions to Python, and then eventually at some point was realized in this official C API. So you have this PyObject star type, you have a bunch of other types like PyLongObject, you have a bunch of official functions, and that's the C API. When I talk about the C API for Python, it's this. And we'll see more about that in a second. And it's kind of like the JNI, but it's a little different. The JNI was designed from the get-go, I think, to support multiple JVMs. The C API was just CPython. So let's take a look at an example C API function. This is PyLong as long. This takes a PyObject star, which is the Python heap object, and it converts it to a C long. So you call this when you have an object and you want it to unbox it. And there's some documentation for it. And then part of this, the contract for this function is it'll raise an exception if it's too big, or if it's not an int, or some other error happens. It'll return -1, it'll write something to the thread local storage, and then you have to read from the thread local storage to disambiguate if your thing was actually -1 or if you got an exception. Fine. But that function sort of assumes some stuff about how CPython works, about how the Python works. PyObject star is a CPython object. It does not move. They are fixed for eternity. And they also assume that you have all these other functions like PyErrorOccurred implemented in your runtime that just read from thread local storage. It doesn't take any parameters. It doesn't take a thread state. It just has to look it up. And there are other Pythons like PyPy. PyPy's goal is to make Python fast. It has a really advanced JIT, about 20 years old, 20 years of research in there. And it does support Python C extensions, but it has a totally different object model. So because the CPython C API was developed for CPython, and PyPy has a different object model, it's got a moving GC. Objects just move around. And it also has a totally different object layout, right? It's not PyObject based. It unboxes things sometimes, or when it does box things, they have totally different memory layouts for performance reasons. You don't have PyObject star. You just don't. So it has to emulate PyObject star and all of these other functions, and that bites. That really hurts for performance, and also it's just a lot of code to manage. Here's an example of why it hurts for performance. You might be in the JIT running some Python code. It's an optimized trace, and it's basically unboxed all these numbers, and everything's fine. And then you call a C extension function. And you know it's a C extension function, so you have this whole path of stuff to talk to it. And the C extension function speaks C API. It does not speak PyPy. So, okay, you're in the JIT, you pass it a number, you box the number into a PyPy heap object, and then you say, okay, well, we have to make a C API object, PyObject star, and then you pass it to the C extension. The C extension, its interface generally is you pass it an array of objects, and it parses them itself. So then it goes and it unwraps the PyObject star, it does something, and then it returns a result. And the result, it boxes to fit the C API contract, and then that goes back to PyPy, which unwraps the PyObject star into its heap object, and then it goes back to JIT code where it unboxes the integer to a C integer. And that's a lot of administrative overhead. That sucks. So let's take a look at how that works for a very, very, very simple example. You have a C extension. It's called AC extension because I'm very creative. It has an inc function that takes a takes an integer, and it increments it. It returns a new integer with 1 added to it. So this is Python code. This is C API code. You can tell because this one has curly braces. And the way you register your functions is you have this array of structs, and it's the inc. So you've got an inc string, and it points to some function pointer, also called inc. And it has this thing called meth_o, which I've bolded. You don't need to worry about the specifics, but meth_o says it takes 1 argument. Okay. And the manual argument parsing this is what this looks like. There's this required boilerplate where you say, here's the 1 argument, unbox it. Maybe something happened. It wasn't actually an int. Maybe it's, out of range, blah, blah, blah. You propagate the error, you return null. And then you call the bolded stuff, by the way. This is the only real work in here. You call your real work function, which adds 1, returns, and then box it again. Okay. Very small amount of real work for a large amount of overhead. For more arguments, it's even worse because you don't have these variadics that, you don't go C variadic. What you do is you pass an array of PyObject star, so PyObject star star. We're now 2-star programmers, and then the number of arguments. And then you go through and did you get the right number of arguments, pull out a thing, extract a float, blah, 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 blah. Do your real work of adding 2 doubles, box it. Even more administrative overhead. Really, really fun. This is what's called meth fast call. It's fast because in CPython, you don't allocate this array, you just take a view of the stack, which is all PyObject star. And that's the core of this, is that PyPy already knows this stuff about its objects. Why would you need to parse the arguments? If you already know this stuff, you already know things are ints from your traces. There's this really advanced optimizer doing all this static analysis. But none of these checks are visible to PyPy because they're all in this, this is this thick line here. This is C extension code. None of it is visible to PyPy. This all happens in this opaque blob that PyPy can't see into, so it can't remove the checks. It just has to call into this thing with this contract, the C API contract, and you lose. Bummer. So it has to manufacture this PyObject star because it can't do anything about all of these checks and all of these interfaces. So we said, all right, you could do a bunch of static analysis, or you could add types. You say, here's a type descriptor for this inc function. It takes 1 C long, and that's an array that's terminated by -1. And you return a C long, and the underlying function is this thing called inc_incpl, which is doing the real work. And then you sort of stuff it behind the name. So instead of putting a string literal, you say this is the inc field, and then if you have this bit set, the meth typed bit, look behind the string. There are some types. And the nice thing about this is since it's stuffed behind the string, it doesn't actually break any API. You can't expand the struct because that would change the size of these arrays, and other Python implementations and CPython and stuff would break on these C extensions. So that's cool. And then once you have these types, the nice thing is you just use them in the JIT. So you read that struct once you load the C extension. You say, okay, this function pointer, you pass it 2 longs, or you pass it 1 long, and you get a long back. Skip all the stuff. Don't box it. Don't check it. Don't make a PyObject star. Do not pass go. And this is what the code looks like. This is what the transformation of the code looks like. So previously, in the JIT, you might do something like, are you an int? Okay, great. We'll just do the unboxed thing. And because you have this nice fancy optimizer, you can say, well, we already know it's an int. Skip that check. Oh, we already know it's unboxed. Skip that. Don't need to box it either because it's just going right back into an unboxed int variable in the trace. So all of this stuff in the optimizer gets blown away, and you end up with this nice clean call. It's an indirect call still, most of the time, or actually it might even be a direct call to a C function with unboxed arguments and unboxed return. So here's an example of a micro benchmark, and you can tell it's micro because this is the entire benchmark. You import a C extension, you call inc a billion times, and you measure. Did it get faster? This is the worst possible case. You have a tiny C function. It's all administrative overhead. Did we do any better? Let's see. Turns out yes. So this is a big box and whisker plot, but the things are very compressed because there's not very much variance. We have a bunch of Python runtimes. GraalPy is on the left, 2 PyPys, 3.10, and then 3.10 that we optimized, PyPy 3.8, and then a bunch of CPythons. And you can see that there's some performance variation in the CPython. GraalPy does pretty well, and PyPy 3.10 before our changes did terribly, like really, really abysmal. This is 160 seconds to do 1 billion ads. Not great. But after our changes, 2 seconds. That's pretty good. That's like 60 plus X speed up. Again, this is the worst case. This is not a real benchmark. Nobody writes code like this, and if they do, they shouldn't be writing code. But it's the worst case gets a lot better, which is pretty nice. And so the consequences for PyPy, you might say, well, does this break anything? How do I know it's correct? Blah, blah, blah. And it's pretty limited blast radius because it's opt-in. You have to add these types. If you don't add the types, it doesn't break. It also doesn't get faster. And so yeah, it's 60 to 80x, but on some benchmarks and only if you're writing code like that. But it's still, your effect radius in your JIT compiled function is much smaller. You can do a lot more optimization around the C calls. But if you don't opt in, nothing changes. No breaking, no performance changes. And then for other Python VMs, we see that in GraalPy'22, things are pretty fast. But in GraalPy'23, they dropped this thing called Sulong, and their runtime it actually didn't even finish in our benchmark. So you run this thing 1 billion times, and GraalPy'23 never finishes because they removed the thing, their technology called Sulong, which I'll talk more about in a bit, that makes this fast. So can we help other runtimes? I think yes. GraalPy could use something like this. CPython doesn't need it yet, but they're starting to build a JIT. Right now they have it's called a copy and patch JIT. It's kind of a baseline JIT. But as soon as they start doing more advanced JIT tech, they're going to start unboxing objects, and then they're going to run into the same problem. So it will bite them eventually, and they could use these type annotations. So the takeaways from all of this is that optimizing across language boundaries is hard. Raphael knows that as well as anybody. And if you just add type information, you get a lot. You get a lot of mileage out of a couple annotations. And it doesn't break a lot. So I think the first implementation of this, we had 1 or 2 bugs, and then it was, it's only 60 lines of code, it turns out, and it doesn't break very much. And then if you don't want to add all these annotations, you don't have to, because the thing we're working on right now is, say you have Python code, which a lot of people do. Python is it's a different language. It's sort of 2 things. One, it's a binding generator, so you can use it to interface with existing C functions, or you can also use it as sort of a Python compiler. And the nice thing is it has these types, and I've bolded them because they're not normal Python types. They can be trusted. They are checked. You cannot lie to Python. And the nice thing is we can take those ints and generate the type stubs for you. So no need to write them by hand. Use Python. Your code automatically gets faster. That's fun. And that's it for us. Papers on ACM. This is a QR code for the paper. Call me, beat me. And this has been Dr. We Notice. Thank you.
Okay, thank you, Maxwell. We already have 2 questions.
Hi, I just wanted to ask about I think it was like 2 slides ago,
Yep.
where you mentioned that it was like an opt-in, I don't know if that's the right slide. Yes, and you said nobody has this right now. Is that just because there's no motivation for, like, I guess because you haven't published it yet? Or I guess I wasn't understanding what that meant.
So it's not merged into mainline PyPy.
Okay.
The reason is twofold. One is, writing the types is kind of onerous, and we'd rather generate them from Python. And the second thing is we're working on a sort of more expressive type protocol. So right now, what you can say is you can promise, you pinky promise within the type information, this function never raises an exception, and you get, no exception checking. But that's kind of or you can say, well, it might raise an exception, and then PyPy has to check. But we'd like to have more stuff there. Like maybe it's not reentrance at all. Maybe it's, you know, I don't know. You can express memory effects somehow. So there's just more work we want to do before merging it.
Thank you so much.
Any more questions?
Thank you for the really interesting talk. I was wondering, so the types in Python are complicated.
Yes.
So are you mostly handling the nice underlying C types, let's say, or what are you targeting in this area?
That's a good question. Right now it's just C types because the perf head is in unboxing and all this other stuff around them. And if you're passing in a Python object, then you're probably going to do weird Python things to it. So you're going to take the perf head anyway in the C extension. But there's some stuff that you can do, like if you promise you never get, I don't know, you might, you know, the exception stuff still, like maybe you never raise, you can guarantee somehow you wave your hands, you never raise, you can avoid some TLS lookups, but right now it's just C types. Well, there's also none. We do support none. You can say the return is always none. Great.
Any more? Okay, thank you, Maxwell.
Thank you very much.
Now the last talk of the session will be given by Patrick Chapman. The floor is yours. And Patrick is going to talk about interleaving static analysis with LLMs.
Hello? Okay. All right. Yeah. So thanks for that introduction. So at a high level, the very basic question that we're trying to answer today is, can the introduction of LLM prompting lead to more learned program facts? And so more specifically, in our case, can a static analyzer be interleaved with LLM prompting? And so can program facts learned via an LLM assist a static analyzer? And can the program facts learned via a static analyzer assist an LLM? So by static analysis, we're referring to those analyzers that are typically used in bug finding applications, where you give some source code, you iterate over some number of program points, of course, you run your analysis, you update your program facts repeatedly, and then of course you have your final set of learned program facts, which can include things such as types, error specifications, and null pointers, which can then be fed to like bug checkers to find violations related to these program facts. So by LLMs, I'm sure we're all aware of them and have varying opinions on them, but they're just large language models where they're given some input and then they're trying to predict the output, the next sequence of characters. So given this natural language prompt from the Iliad, it outputs a remainder of a quote. And of course, it also extends to programming languages now. So given a Fibonacci function signature, it outputs an implementation. So more specifically, a lot of the actual things that people care about with LLMs are, what do you provide a prompt in order to generate useful output from an LLM? So what is the high level? What do these prompts typically look like? So I guess here's a very high level example with program analysis. So you give it some problem description and you can include background knowledge, so maybe various definitions that could be useful. You also can include question and answer examples to the LLM to guide the output. And this example would be a single shot where multiple would be considered few shot. But you can also include natural language explanations called chain of thought explanations in order to hope that you can guide the LLM to more usable results. And so, of course, then you actually have your main question of interest, which the LLM will attempt to answer. So for interleaving, what we do by how we interleave program analysis, or sorry, static analysis in LLM prompting is so this unknown, in this case, I'll demonstrate an actual example of this, but at some point, if you come to an unknown, you don't learn anything useful, you instead just prompt the LLM to, of course, for that information, and you update your program facts, and then you repeat iteratively over those program points and continue running the analysis. So specifically, I'll talk about how we can apply our approach to a static analysis for error specification inference. So this deals with error handling in C, since C does not use exception handling. A lot of times, many systems or many programs use the return code idiom, which is where specific values are returned on error. And so error specifications are just the function and its values returned on error. And so, of course, how can you know what these are without manual inspection? Static program analysis, more specifically error specification inference. So specifically, we use the easy static analyzer, which uses abstracted interpretation. So of course, it just abstracts the return values, like on the signed domain, like a signed lattice, where the bottom indicates unknown in this instance, the top indicates all values, and the empty set in this specific analysis indicates like an infallible function or a function that does not utilize the return code idiom. So what's the actual input to this static analyzer? So it's an initial set of error specifications, status codes, and error-only functions, and the actual output is the set of learned error specifications, which can then be passed to things like bug checkers. So for error specification inference, the workflow looks like, so we iterate over functions starting at the bottom of the call graph, performing a fixed point on each strongly connected component. So at each function, we run on easy, and if the output is bottom, then we prompt the LLM, and we ask it for any error specification. And if we can use that learned program fact, then we can update the error specification and then repeatedly run the rest of our analysis. So what does the actual prompt consist of that we're passing? So essentially, very, very abstracted version of what we're passing, but essentially I'm just asking it to determine the error specification of a function. And so, of course, I actually have to explain what an error specification is, but also like idiomatic practices, like explaining the return code idiom, the actual abstract domain we use, and the status codes and error-only functions relevant to the program under analysis, as those are global. And so we also provide return code idiom illustrative examples that are program agnostic, and we also provide chain of thought explanations like about the return code idiom and explaining them. But we also provide few-shot examples of error specifications of called functions already learned during the analysis. So these come from either easy static analyzer or previously from the LLM already. And the actual question we provide is just the function definition, or in the case of like external library functions or third-party functions, we don't actually have the definition of these, and so we just provide the name of those. And for our few-shot examples for those, we actually just provide a global set of error specifications. So of course, with LLMs, there's always the issue of hallucination, and we can't make guarantees, of course, but we do attempt to limit some of the imprecision, and we do provide 2 checks for easy that we can do from learned facts. So like we can check against success values, obviously, known success values that we can calculate during the static analysis. But we also check against the known return range. So if, of course, if the LLM provides an error specification outside of the return range, you know that that's not correct. But we also explicitly reprompt the LLM to remove any known success values, as the check against the return range isn't perfect, and also to remove any error value not confident in. And these were just chosen primarily because they just seem to work. And so here's an example from Embed TLS, which is implementation of SSL and TLS, and it also has some cryptographic algorithms included. So if we look at this left side of the call chain and we look at this leaf node, this is a third-party function, and if we don't provide it as an initial error specification, Easy won't know anything about it, and it returns -1 on error. And this becomes an issue later on in the analysis, as this netset block function returns that call value. And so in that case, well, why don't we just prompt an LLM? And since we provide the abstract domain and the other background knowledge, an LLM, in this case GPT-4 Turbo, is able to translate that to the abstract domain that we use for Easy. And then we can update the program fact, get it correct, and then ultimately Easy can use that to get the netset block function. So let's take a look on the right side. So in this case, this lower get tag function, Easy does infer correctly, but however, Easy in this function, or Easy later on, is unable to infer the attribute type value function for whatever reason. It's more of a black box in this case. But later on in the analysis, it will get the get name function wrong again, like the last example, because it returns the function called return value. So, like I said, whenever it's bottom, we're going to attempt to pass the function definition to the LLM. So we'll also demonstrate why they're just not perfect by themselves. So let's say that we don't pass that get tag function that Easy already learned. So the LLM thinks that it's not 0, which if you look at the code, you can understand why it might think that, but that's actually incorrect because it doesn't return positive values on error. And of course that can affect later on in the analysis. And so it understands that the error code is negative. However, a negative plus a positive or a negative, it ends up just being top element, which is incorrect. So how about if we, of course, add that the learned error specification from Easy? Well, we see that the LLM actually is able to understand that a negative plus a negative is still a negative, and that the error specification here is less than 0. So as we can see here, the Easy is able to help the LLM, and then the LLM is able to help Easy on this part of the call chain. So for our actual research questions that we want to actually ask is, so what's the baseline performance of Easy? So how is the static analyzer doing by itself? And then what is the actual effect of interleaving? So what is the precision recall in F1 for our approach compared to the baseline? And also to note that error specifications match exactly. So for instance, less than 0 is not correct for an error specification that's less than or equal to 0, even though it is a subset. So for experimental setup, we selected Okay, hello? Okay. So, right, so for our selected LLM, we used GPT-4 Turbo at the time, and we selected 6 benchmarks that you see on the left. And then for the actual initial domain knowledge that's input to the static analyzer is demonstrated on the right-hand side of that table. So for the baseline of easy, of course, higher is better, but the 6 benchmarks are listed at the bottom. And so the left, of course, the left bar is the precision, middle bar is recall, right bar is F1. And the precision ranges from just under 65 to 97 for zlib, where the recall is down to 10.3 for pigeon, which also has the highest number of third-party functions. So these can't be statically analyzed by easy. And also embed TLS has the highest. And of course the F1 ranges from 18.4 to 89.5. So our approach improves the recall over the baseline. So for the increase, so the left is the easy and the right is our interleaved approach. So as you can see here, with pigeon being our lowest, highest third-party percentage, we see quite a decent increase there. But we also see an increase in net data, which does have a lower percentage, but still has a good mix. But we do also see a slight decrease in precision, of course, where the pink bar on the right is the delta. So these are the uniquely learned error specifications from our approach over the static analyzer. So as you can see here, the largest drop-off is within Apache. And but we also do see instances where we do improve, like in net data where we had a relatively low precision to begin with. But more importantly, we increased the F1, so the harmonic mean between precision and recall. We see, of course, the biggest increases being in net data and pigeon again. But also in HTTPD, even though we did lose precision, our F1 increased quite significantly. So in conclusion, we've presented an approach for interleaving static analysis and LLM prompting, and we've demonstrated that facts learned via one another can assist one another. We've also demonstrated that our approach can enable us to learn more error specifications, where we increased our average recall from 52 to 77.8, increase in F1 from 0.61 to 0.8, and then we maintain like relatively similar precision with a drop-off from 86.6 to 85. And thanks. And of course, our GitHub for this tool, I still have to merge something to master, but that is the link for our tool. Thanks.
Any questions? Let's try the microphone again.
Thank you. Very nice idea. So I'm wondering if you have some LLM hallucinations and you take them into your analysis, would you recognize that later on during the analysis?
So, I mean, I would say the most common like problem that I've seen is the LLM will provide a chain of thought explanation that clearly and successfully distinguishes error values and success values, but the error specification is the combination. And that's just not right, and it's annoying. And so like we have those success value checks, and like telling it to remove the success value eliminates a lot of that. And then also the return range can help with some of that too. If it's just wrong on the success values, like out of the return range or whatever. Does that kind of answer?
I'm not sure. I was wondering, so basically you take those results into your analysis for the next round, right?
Yes, yeah.
So would you see in the next round that something is fishy here?
No, so like we do that like we do those checks beforehand before we update, and then we attempt to update, and then we just continue on in the analysis. Okay.
Further, okay.
Thanks. I have a following questions about since you queried the LLM on the fly, so have you checked the performance of this analysis since if you interact with LLM and especially GPT-4 is not a very
Yeah,
very
well,
fast.
especially, yeah, because this is over the network, right? Because it's GPT, which does slow it down. We've done some, so for instance, our longest running just on the static analyzer was like approximately 7 minutes just from the static analyzer. But introducing GPT-4, and of course the request with those was closer to 30 minutes. So it does, yeah, increase the time quite a bit. We have been trying to do some using the offline models like Code Llama and all the other ones. And the only issue is like those did not perform as well. And like we were having some issues with the models in general. But like if we ignored that, they did run faster, like closer to 10 minutes, like 7 to 10. If that makes sense. So
Thanks.
Yeah.
And if I can add to this, ignoring the execution times, in general, more or less a metric on how many of these interleavings you need to perform between the NLM and the EZ before reaching the final results that you can no longer update, if you can give a metric on that.
Do you mean like for one function or just like throughout the entire?
No, throughout the entire analysis, a metric. Is the LLM query like thousands of times for a single analysis, or is it just a couple of interactions?
So if the benchmark is like on the scale of like thousands of functions, we could see like hundreds of queries to the LLM. And like a lot of times the LLM might not produce anything useful. So, yeah.
Okay. Last question.
Just in this case, when it does not produce anything useful, how do you find out and what do you do?
Well, sometimes it just does won't even output an error specification, but also we also include like LLMs may generate non-parsable output for our instances, and we consider that to also be unknown. And so if it's unknown, we just continue on the analysis as we would normally, just iterating to the next function. So does that make sense?
Yeah, it does. And I would prefer to not use anthropomorphic terms to talk about the token predictor. Better to say that they are and predict something than it reasons about it.
Yeah. Yeah.
Okay, so thank you, Patrick.
Yeah.
And with this, we conclude the session, and we can now move to the lunch break.
Hello, everyone. So we are ready to start the third session. My name is Cindy Rubio Gonzalez from the University of California, Davis, and I will be chairing this session. So our next keynote speaker is Manu Surdaran. He's a professor of computer science and engineering at the University of California, Riverside. And today he will talk about lightweight resource leak verification and inference.
Thanks a lot, Cindy. Can everyone hear me? Yep. Great. So I'm very happy to be here. Thank you for the invitation. This is work that was done with several collaborators. I want to specifically call out those who were students or postdocs when they did this work. So Nargis Shadab, my recently graduated PhD student who's now at Oracle. Martin Kellogg did some of this work when he was still a PhD student. He's now a faculty. And Preetham Garat, when she was a postdoc at Microsoft Research, did a lot of the work here. So I wanted to give proper credit. The collaborators were absolutely essential here. Okay, so resource leaks. What is a resource leak? In a language like Java, of course, you have the garbage collector to help you manage memory. But even so, there are particular types of resources where you should be explicitly doing a function call to release that resource. You can't just rely on the garbage collector to manage it. So here's an example. We have a socket, and you're supposed to close it. And if you forget to call close, that leads to a resource leak. There's some underlying operating system resource that doesn't get reclaimed in a timely fashion. And besides sockets, other resources that you have to manage explicitly, including things like file handles, database connections, there are potentially many other examples. So any type where you explicitly need to call some finalizer function before it goes out of scope is potentially subject to resource leaks. And resource leaks cause a lot of real-world problems. Resource starvation, they can cause slowdowns or system crashes, even denial of service attacks, right? If someone knows a way to like force your service to just allocate more and more resources without releasing them. And these are pretty nasty to try to debug with testing, right? Often these won't manifest in an obvious way with your unit tests or even your integration tests. They'll manifest when you've been running your service for a week and all of a sudden it's getting really, really slow and you're not sure why. And so, I don't know, you end up having to reboot it or something, and then a week again, it happens again, right? We'd hope to do better, right? So for many, many years, people have worked on automatic techniques to try to statically detect or prevent resource leaks. So I can give a very rough categorization of existing approaches. We can kind of put them into three categories. The first is heuristic tools. These are often built into your IDE. Eclipse has a resource leak detector. IntelliJ has a resource detector. And these tools run very quickly. They can give you reports without taking a long time. But in our experience, they're both unsound. They miss real issues. And they're also kind of imprecise. They report a lot of false positives. So hopefully we can improve on that. Another approach, which has been pursued in multiple different systems, is whole program analysis. For example, there's a very nice paper from ICSI 2010 by Meena Torlak, Satish Chandra, effective interprocedural resource leak detection. And people have built on this. Grapple is a recent system that does this kind of whole program analysis. Tends to be more sound, catches more issues, more precise than the heuristic tools, but it can take a long time to analyze a big program. We'll show for Grapple, it's on the order of hours for larger programs. So that's not great if you're trying to, fit this into your developer workflow. And finally, and more recently, there are techniques like ownership types, right? As in the Rust programming language, which basically, if you're using it in the intended way, they get rid of resource leaks, right? You get various guarantees that when an owned pointer goes out of scope, it's going to be finalized and closed properly. So this is, sound and quite precise, but we're interested in tools that'll apply to Java and the type of aliasing restrictions that are required to fit your code within the Rust type system. It's kind of very difficult to retrofit that onto existing Java code. So what would we like here? Kind of an ideal checker for these kinds of resource leaks. We'd like it to be sound, or at least, soundy, catch as many of the real bugs as we can. Of course, we want it to be precise. We'd like it to be really fast, right? With modern development workflows, it would be great if you could run this as part of your continuous integration and report issues before they even land on your main branch. And we want it to be applicable to existing programs written in Java or C#, those style of languages. And just looking at this list, you might be wondering, hey, it's pretty hard to accomplish all of these things with pure static analysis. And I'm not going to claim that we've done all of these things simultaneously perfectly, but I think what we've done is found a new point in the design space that I think is valuable in many scenarios and is worth exploring and trying out further. So what did we do that was different? Like kind of what are our kind of new ideas? So one key insight is that we figured out that we're able to do very targeted reasoning about aliases, specifically if you're trying to solve the problem of preventing resource leaks. So we've defined this class of type state properties called accumulation properties. And the interesting thing about them is that you can do sound type state checking without doing a whole program alias analysis. Now, it doesn't mean it's going to be precise, but at least you can have a core sound technique, and then you can try to improve its precision by layering on targeted reasoning about pointer aliasing. Okay? So that's kind of at the core of our approach. If you can kind of track the right set of must aliases, you'll be in good shape. But that kind of raises the question, well, how do we know which of these aliases we actually need to track? And here, I've been doing a lot of work over the last few years on pluggable type systems, right? Where you add some additional annotations to your code and it enables checking of correctness properties kind of within the compiler, almost like a type checker. And that's the approach we use here, where we've defined sets of code annotations that expose the really important aliasing and ownership properties to get more precision in this resource leak checker and capture the patterns that are used in practice. So this is great because now when we're doing this as a type checker, we can do modular checking, right? We can type check one file at a time. Incremental analysis basically comes for free. It runs really fast compared to whole program static analysis techniques. And now there's always the question of, well, what about existing code, right? I've got a big code base. Who's going to go through and write all these annotations? So after we developed this checker, we also developed an inference technique. I call it optimistic inference, and I'll tell you why later, that we showed is pretty effective at easing this initial annotation burden if you have a big code base and you haven't been running our checker yet. You can run the inference. That should give you a good initial set of annotations, and you can kind of go from there. So I'm going to tell you the technical details of some of the technical details, anyway, of what we've done. But this is the work I'd like to describe to you today, and it's available for people to use. So it's available as part of the checker framework. It's called the Resource Leak Checker, and there's also an implementation RLC Sharp for C# code built on the CodeQL platform. So I'm excited about this work. And first, I'm going to tell you about the core pluggable type system that we defined that we use to verify the absence of resource leaks. And then finally, I'm going to get into some detail. We see how much time I have left on this inference technique to automatically add the necessary annotations to your code. And I forgot to say it at the beginning, but I'll say it now. I'm really happy to take questions at any point during the talk. No need to save them for the end. Just raise your hand. Let's try to keep this interactive. Okay, so let me first talk about the lightweight resource detection based on pluggable types. And taking a step back here, the broader context of verifying these types of properties falls in the field of type state checking. And in type state checking, you have objects that transition between different states as you perform operations on them, but certain operations might be illegal in certain states. So here is automaton, a type state automaton, describing what are the legal and illegal transitions for a file object. And you can see that whenever you transition to error, that's an illegal transition. So if you call open on a file and then try to open it again, you end up in the error state, right? So that's one of the things that you shouldn't do with these file objects. So the goal of type state checking or verification is to check that in your program, none of your objects can ever transition to this error state. Okay? So this is, again, a problem that's been studied for decades. And the key challenge here in doing type state verification at scale is dealing with pointer aliasing, right? Because the problem is that your object state might transition through any alias of that object. Doesn't always need to be the same variable. Here's an example where we have 2 calls to open. So this is a problem, but it's through 2 different aliases. So you have to do alias analysis to keep track of this stuff. And the previous approaches, I gave you this breakdown before. You can also kind of break them down by how they handle this problem of pointer aliasing. So the heuristic bug finding tools, for the most part, just ignore aliasing. And this is what leads to them being both unsound and imprecise. Then we have the type-based alias control, right? So this was the ownership types in Rust, basically give you strong restrictions on how you create and use aliases. That helps a lot in verifying these properties, but it's hard to migrate existing Java code to use that kind of discipline. And finally, there's whole program alias analysis, right? Just try to track all the aliases, but this is hard to scale and hard to turn into an incremental analysis that's suitable for CI. So we looked at this problem, and we observed that there were certain types of properties where you can actually do verification without doing a whole program alias analysis. Now, doesn't mean it's going to be precise, but it'll be sound, okay? So that's kind of the basis of this work, this idea of an accumulation property. That's what enables this kind of modular type-based checking. I'm not going to get into all the formal definitions of what is an accumulation property. You can see our eCoop 2022 paper for all the details, but the intuition is that you have type state systems where certain operations enable some other operation of interest, right? They make them legal, and once that operation becomes legal, it can't be disabled, okay? There's nothing else that's going to make it illegal. So again, I'm kind of hand-waving, but you can ignore the aliases because once you see that this, how do I put this, right? If you ignore the aliases, then you're going to get false positives, right? Maybe some other alias made this operation legal and you missed it, so you report a false positive, but you don't get false negatives, right? All you can miss is kind of things that made the operation legal, but you never miss an operation that makes it illegal again, because that's not possible. So how do resource leaks fit into this world of accumulation? Well, here's our assumption about a Java-like resource. We assume that, you know, it's in an open state, you call close, and then it gets closed, and we're not trying to detect like kind of the equivalent of a double free error, right? We assume closing it multiple times is fine. So what is the operation that kind of becomes legal? If you squint, it's basically this operation of going out of scope, right? Once you close a resource object, then it's allowed to go out of scope without leaking. But if you allow it to go out of scope and you lose all the pointers to it before you've closed it, then that's a bug, right? So once you've closed it, there's no way you can kind of unclose it and cause a leak again. So it's an accumulation property, and that means that if you want to build a sound resource leak detector, again, ignoring precision, you don't really need whole program alias analysis. And it's very simple. I'll just walk through a simple example, but the core leak detection approach is to just look at different references, different variables, compute what methods are required to be called on those variables, you know, methods like close, and then you compute what methods are actually called, and then you look at the places where the object might go out of scope and see if there's a mismatch, right? If there's some required method that hasn't been called yet. So here's a simple example with a socket. So in terms of what's required, we call that an obligation. So here, with this new socket object, there's an obligation that you need to close it, right? You need to call close on S. And of course, we can very easily do a static analysis to keep track of what methods have actually been called on S. So at this program point, nothing has been called yet. And then after this program point, close has been called. And now with this information, we can look for errors. So like right here, we're overwriting S, right? So that's potentially making the previous socket object go out of scope and close hasn't been called yet. So that's an error. Whereas down here, after this call, we're good to go because we've closed the reference. Okay? So this is very simple. It's actually sound, but you'll see that it's way too simple, right? So if I change the code like this and close s via this variable t, the simple technique that I just defined to you will now report an error, even though this code is kind of obviously fine. So it's not precise. So this is where we need to do our targeted reasoning about aliasing to regain enough precision to make this useful. And we have kind of a suite of techniques that we use to regain this precision. This local must alias analysis is very straightforward. It's just a must alias analysis within a single procedure, nothing too interesting about it. So here in this talk, I'm going to focus on these two techniques, the lightweight ownership and this idea of resource aliasing. So first, let's look at the lightweight ownership. So in this example, I have a method close socket, which takes in a socket and then it closes it, okay? And here I have a call to close socket passing in a variable. Now with the analysis that I defined before, it has no knowledge of what's going on inside this close socket function. I should say that basic analysis was intra-procedural, so we're trying to avoid doing inter-procedural analysis wherever possible to stay within kind of the type checking modular approach. So it doesn't know what's going on. It's going to assume that after this call, I still need to call close on my sock. So what we do here is we add an annotation. We call it owning. And what this tells the analysis is that this method is promising to take care of the call obligation on its parameter. It's promising to close it. And what our checker does is kind of transfers this obligation over here, right? So at the caller, it says, okay, I'm going to assume that close was called. But now inside this method, it's going to check and make sure that close is always called on the parameter. Okay, so this is sound because it's just a hint for the checker, right? It doesn't remove any obligations. It's just telling the checker a hint as to which reference is going to be responsible for disposing of this resource. That's how you're going to call close. And the key difference between this kind of lightweight ownership and what you see in a language like Rust is that this doesn't in any way restrict the privileges of other aliases, right? So you can go ahead and have whatever other aliases that aren't annotated owning, you can do type state transitions with them. It doesn't matter. This is just a hint to our checker specifically for detecting resource leaks. This is why we call it a lightweight ownership transfer. And it's much more in line with the sort of aliasing patterns in Java, right? People are not careful about what aliases they create to objects. So just having this lightweight technique that's good enough for finding leaks is really important. And we also support writing owning annotations on fields. And I'll show a more complete example with that in a couple of slides. So that's one of our techniques. Again, we're kind of telling the tool which alias is important for trying to figure out whether a resource gets closed. Another key technique we called resource aliasing. So you see examples like this a lot in Java code, right? I have a socket, and then I get its input stream and wrap that in an input stream reader, and I've got a variable now pointing to that reader. And the question is, which of these should be closed, right? You've got two references now to two different resource types. And what happens very often in Java is that you have these wrapper types where you can close either one of these, and that's sufficient to release the underlying resource, right? Another example is like a buffered input stream, right? You can close the buffered input stream, which is wrapping some other input stream, and that will kind of go into the wrapped type and make sure that its resources are cleaned up. So this is the pattern that we're trying to capture with this notion of resource aliasing, right? So these are not must aliases, right? Obviously, they're different objects, but from the point of view of cleaning up resources, we can treat them as if they're must aliases, right? Which means that if you call close on either one of them, that's going to satisfy your obligation, right? So we treat them as must aliases for the purpose of checking for resource leaks. And other works have done this in the past, but the way they did it was kind of baking into the tool a list of like all the wrapper types in the standard library. You know, buffered input stream, filter input stream. They list them all out, and then they bake in reasoning for those types into their analysis tools. In contrast, we have a mechanism via annotations. It's a resource alias annotation to create your own wrapper types, right? And you can annotate them with these resource alias annotations, and we can actually verify that it is a proper wrapper type, that it's properly disposing of the nested resource. And so this is much more flexible. And then we can use this annotation in our models of the standard library to capture the cases that are in the library. So it's kind of a unified mechanism that you can use in your own code as well, which comes up a lot in real world code. People write these wrapper types all the time, so it's nice to have this mechanism. And let me show a detailed more example, though again, I welcome questions at any time, but maybe we'll have questions. Here's a more detailed example. I hope the font size is readable, but basically I have this class, MySQLCon, which is wrapping one of these connection objects, right? So let's assume a connection object is something that you need to close, right? It's like a database connection. So here we're wrapping it, and we write these resource alias annotations on the constructor that kind of tells clients that, you know, if you create a wrapper around a connection, you can kind of close either of them, right? That's what happens here. This code can be verified. In one case of the if, we close the connection directly. In the other case, we close the wrapper, and this passes our checker just fine, because we know that they're essentially must aliases for the purpose of closing resources. So, but we need to check that this type is doing the right thing. So the way we do that is that we annotate this field as owning, right? So this is the reference that's going to be responsible for closing this connection. And the way it's going to happen is that this MySQLCon type needs to define a finalizer method that takes care of closing that, right? In this case, it's this dispose method, right? So dispose is the method which, via some other method, we have an annotation says this is always going to call close on the con field, right? And we verify that this annotation is correct as well. And then finally, we have a top-level annotation that tells the users of this class, if you're creating a MySQLCon object, you have an obligation to call its dispose method, right? Because that's the thing that's going to get rid of the resources that are managed by this type. Yeah, question. I think, do we have a mic?
So the resource alias annotation is the second one, just signifies that this is the alias for this object. Is that correct?
Exactly. Like you might have multiple parameters in your constructor, and so you need to say which one is the resource alias with the new object.
Mm-hmm.
Yep.
Any other questions?
Suppose I use a library. How do I add annotations to the source code of the library, because I don't own it? Can it be done externally via some models, or what do I do?
Yes, so we've built this all on top of the checker framework for Java, and it has a mechanism for essentially writing what are called stub files, where you kind of copy the signatures of methods from the library, but then you can add your own annotations, and when we're checking, we kind of use those annotations from your stub. Now, that is, we don't verify those annotations. Those are trusted. So if you actually wanted to check that those were correct, you would have to then go annotate the library source code and run the checker on that library. But there is a way, if you don't own the library, if you want to trust some annotations that you wrote, to kind of plug them into our tool. And that's in fact how we handle the Java standard library, is with these kinds of stubs. Okay, so it's important that we don't just trust these annotations. We do actually try to check that all these invariants are being respected by the type. So let me just give you a hint. Maybe I can flip back and forth of how we verify. What are our rules for verifying these annotations? So if I have a final owning field of type T inside class C, then, okay, we look and see. T is annotated must call M, right? So M is the method that always needs to be invoked on on these objects, and then the enclosing class C is annotated must call N, right? Then we want to check that this N method is always going to call M on the field, right? So there we just check for the annotation that that N method is always going to call it. So here, this is the owning field. The method that always needs to be called is close. So we need to check that this dispose method is always going to invoke close on the field. And so that rule is satisfied in this case. And then what about resource alias annotations? We have a bunch of cases for that. So here for a constructor, we check, okay, the class should have exactly one owning field, right? Because if it has multiple owning fields, you can't be a resource alias for all of those things, right? You kind of have to pick one. Otherwise, it's not going to be equivalent, right? This class is managing multiple resources, and yeah, it doesn't work. So there's exactly one owning field. The constructor should always write its parameter into that field. Okay, so we have that satisfied here. There's exactly one owning field, and this method is always taking the thing and writing it in here. So that's sufficient along with our separate verification that that owning annotation on the field is correct. Yeah, another question.
So do you do verification on the owning annotation itself? Like, because in the Rust, the ownership requires a quite complicated borrow check stuffs. It's not only related with the function that you annotate, it's also related with the core side of the function. Like if you pass ownership to the function, then you make sure you not access the resource again. So do you do check on that also?
Yeah, great question. So I talked a little bit before about how this is a lightweight notion of ownership, right? So ownership is just kind of a hint to our checker about which reference is going to be responsible for kind of closing the resource, right? Because we're only trying to check resource leaks. So in order to check resource leaks, we actually don't need to do all those other checks that Rust does. Rust is much more restrictive about exclusivity of an owning pointer and not mutating through non-owning pointers and that kind of thing. So we don't need to do that for resource leaks. So now what's the downside? Rust can actually verify the absence of issues like double free or use after free, right? You'll never have those issues in Rust. We cannot check that. So it's possible after running our checker that you'll always close a resource, but then you might try to use it afterward. And our checker is unable to check that property. Okay. So we're going solely after resource leaks, and that's what lets us do this lighter weight checking around ownership.
Okay, I see. Thank you.
Yep. Okay. So no other questions. So let me show you some results from our evaluation. So we looked at some pretty serious programs with some hairy code in them, like Zookeeper, component from Hadoop, HBase. So it was a significant amount of code. And so we found 49 real resource leaks. We reported several of these upstream and got them fixed. The precision is not that great, you know, compared to like a typical bug finding tool. And part of the reason is that we're trying to be sound here. I mean, I can't guarantee our implementation is bug-free, but we're really going after trying to catch all the leaks, and so that does lead to some false positives. Common causes that we saw were cases where you needed path sensitivity to prove that a leak wasn't happening. We don't have path-sensitive reasoning in our tool, at least not yet. Another big issue is like collections of resources. Like if you have a list of sockets and then you iterate through all of them, we're actually actively working on this, but we didn't yet have a way to verify that kind of code pattern. So that's another cause of false positives. So yeah, but we did find, you know, a lot of real leaks. In terms of the number of annotations, we think this is quite reasonable. It's roughly on average one annotation per 1,500 lines of code. And intuitively, it makes sense that you wouldn't need a huge number of annotations for this property, because you only need to annotate code that's related to resource management, like opening and closing resources and passing them around. But if you have other libraries that never touch files or sockets or any of that, you don't need to annotate them at all. So it's not like a pervasive property that it's going to impact every class in your program. So we wanted to do some comparative evaluation. of our checker, that's the RLC, Resource Leak Checker. We compared it to Eclipse's heuristic bug finder, and we ran it in its high confidence mode, so only admit high confidence issues. And we also compared to Grapple, which was a recent kind of whole program type state checker based on like efficient graph reachability techniques. And here's kind of a summary of our results. So first, in terms of recall, and this is under the assumption that we don't have bugs in our implementation, we still found way more real resource leaks than either of these tools did. Like they just give up on a lot of real resource leaks. I think because it's hard to track all the aliasing involved and be confident in the reports. In terms of precision, Grapple did better than us. Surprisingly, the Eclipse heuristic bug finder, even in high confidence mode, had roughly the same precision as our tool. And here again, I think it's because you need to track aliasing both for soundness and for precision, right? Like if you don't know that there's a wrapper type that it's legal to close the resource through that wrapper type, then you're going to report a false positive. Like that's an alias that you need to track for precision. So this I was kind of surprised by. I thought they would be much more precise, but even in their high confidence mode, Eclipse's false positive rate is roughly the same as ours. And then in terms of running time on some of these huge programs, Grapple took over 36 hours. Eclipse is a little bit faster than us. It's hard to see on this chart. I didn't zoom in to show that, but our running time is quite reasonable, on the order of a few minutes. Yeah, question?
What happens if you decrease the confidence that you require from Eclipse? So I could imagine that the recall goes up. Is it anywhere close to your tool then? And the precision will likely go down. Is it really bad, or is it just a tiny fraction?
Yeah, good question. I think when we ran Eclipse in low confidence mode, we were just overwhelmed by the number of reports, and so we didn't have the cycles to do a very careful triage of all of them. I think thinking back, we should have at least checked the recall, so that's something maybe we should go and look and do, but the precision becomes terrible, like absolutely terrible.
Well, obviously, if you know the results from your tool and you have checked that, you can still check whether Eclipse finds at least those. And
Yes.
if it doesn't, then it's out of the question and garbage, but
Yes.
if it does, then it would be interesting what the trade-offs are.
Yeah, so I'm quite confident that this precision bar, because we know what the real issues are, and it was reporting like hundreds more issues, so this is going to go way down. How far this comes up, I'm not sure. In my subjective opinion, it's kind of getting beyond the point of, if it's, 1 out of 20 reports is a true positive, that's getting kind of hard to triage. But yeah, we should measure that and check that more carefully, at least the recall.
A question. So, and about your ground truth. So, what are you using as ground truth?
Yeah, we make the probably unsafe assumption that our tool. So we're ignoring bugs in our tool. We just look at all the reports from our tool, which is intended to be sound. So that's where we triaged all of these reports. So that's what our ground truth is. But there's a threat that like there's even more true positives, and due to bugs in our tool, we didn't find them.
Thanks.
Okay, so that pretty much covers what I wanted to say about our checking tool. Again, it's open source. It's available as part of the checker framework. You can run it on your own code. So now I wanted to return to, oh, sure.
Just one question. So we had a similar problem that in other work that we didn't know how to get a ground truth. So what we did is we looked at all the outputs from all the tools and verified them by hand, and then this would avoid normalizing our own recall to 1. So what if there was something in the Eclipse recall, like one instance that your tool did not have, for be it something you overlook conceptually, some bug in the implementation, because with that you're normalizing your own recall to 1, right?
Yeah, I see what you're saying. We did look at a significant number of the Eclipse reports by hand, but I don't think we exhaustively went through all of them. So for what we did, we never saw a case of like a true positive that we missed, but yeah, we could have systematically gone through every single one to kind of double check that. Yeah, so yeah, I don't know if we were systematic about it, but we did look through a bunch, and we never saw a case where it was a true positive that was missed by our tool. Okay. Right. So we built this checker. Sound, modular implementation bugs. I would argue relatively precise in that we're kind of matching the precision of Eclipse's high confidence mode, particularly given that we're also trying to be sound. And scalability is good, but there's still one problem, right? Which that we rely on these annotations. And although the absolute number of the annotations wasn't that high, it was still, moderately painful for us to go through and write these annotations on these real-world programs. Like, it took several weeks for our case studies. Now, you might say, oh, but you weren't the original programmers, right? And maybe they would have an easier time. But in reality, who knows who wrote that code, right? It was some previous maintainer. It's going to be a challenge to do this all by hand. The patterns are kind of tricky. You have to do a lot of thinking about exceptional control flow paths and stuff. So this is a hindrance to wider adoption, and this is what motivated our work on automated inference, right? Can we build a tool to help in writing these annotations? So that leads to the next part of our talk on inference of resource management specifications. Here, I think I'm going to be kind of brief. Do you know, how much time do I have left? 15 minutes. Oh, okay. I'm doing well. So let me just give you an overview of this approach. So I think you can see that the kind of checking that we're doing as part of the resource leak checker is not just standard subtype checking at assignments, right? We're checking various aliasing related properties that are interrelated, right? According to resource ownership, these resource aliasing relationships, these call obligations. We couldn't just take an off-the-shelf inference tool for pluggable type systems and use it for our system. We needed to develop something custom. And I think probably the most interesting thing about our inference is that it's optimistic, right? Very often, there are bugs in the code that we're trying to do inference for. And so rather than being very strict and only inferring annotations that will be verified, we attempt to figure out what did the developer intend to do. And once in a while, we'll infer an annotation that will not be verified, that will cause an issue, in fact, to be reported, but we still think it's the right thing. And it'll cause the issue to be reported in a better place. And I'll give an example of this on the next slide. So overall, we formalize this as just a set of inference rules. If you look at the paper, it's using like a data log style syntax that we just run to a fixed point. And we actually have two different implementations of this inference. We did it for our existing Java implementation of the resource leak checker, and also we had a collaboration with a bunch of folks at Microsoft. They had actually independently looked at our paper and started working on re-implementing the same checking technique for C#. And then Nargis, my PhD student, went and did an internship with them, and they worked together on completing that checker. And also we got an implementation of inference for C# as well. So let me give you a simple example of this optimistic inference. So here's a cleanup routine that takes in a socket, and first it calls shutdown, and then it calls close, okay? And the issue here is that this cleanup routine is not guaranteed to close this socket, right? Because if the shutdown method throws a socket exception, then this is going to exit before close is called, right? This is kind of a classic type of bug that you see with resources. Really, the close call should probably be in a finally block or something like that. So now, if you think about kind of traditional type inference, right? I think most of the time, it's trying to infer behavior that's reflected in the code, right? That we try to infer annotations that we think actually match what the code does. And if we approached inference that way, we would not infer an owning annotation on this parameter, right? Because it's not guaranteed that this method is always going to close the socket. But in practice, that led to a bad outcome, right? Because potentially you have a bunch of callers who are already relying on this cleanup routine to actually close the socket. And sure, there's a bug here, but if I don't infer this owning annotation, then when I run the checker, you're going to get errors reported at all the client code that's relying on this cleanup method. It's going to say, hey, you're not closing this socket. And that's really not the best output of the tool, right? The bug is really right here that needs to be fixed. So what we do is we do this optimistic inference where we try to mirror the developer intent. It looks like you are trying to close the resource here. Usually when a method tries to close a resource, it intends to close it always, not just conditionally. So we go ahead and we infer this owning annotation on the parameter. And this will not be verified, right? You'll get an error inside this method when you try to run the checker. But arguably, that's where the bug fix is needed anyway, right? That if you fix the bug here, put the close in a finally block, then that's really, I think, what the developer intended to do, right? We can't do proofs about this, but it seemed to work better in practice. Yeah, we have a question?
So I'm wondering, is there any kind of exception analysis that you do for shutdown, or if this shutdown could never throw an exception, would you verify this property?
So in this case, I believe that this is a checked exception, that it's actually in the signature, that it throws a socket exception. Now, even if there were no exceptions declared, there are all kinds of exceptions that it might actually throw. A runtime exception, null pointer exception, all kinds of things. So we try to be pragmatic there. There's a set of like kind of standard runtime exceptions that we just ignore. And we're gonna assume that methods are not gonna throw them. Very often there are actually other checkers in the checker framework that you could use if you really wanna get rid of those exceptions. Like you'd run the nullness checker if you wanna get rid of null pointer exceptions. There's another one for array index out of bounds. But if you assume that any runtime exception might be thrown by any methods, the output of the tool becomes completely useless. So yeah, that's the story about exceptions for method calls. Other questions? Okay, so let me just show you an example of how our inference rules look for doing this inference. So here's a rule for inferring an owning annotation on parameter P of method M. So we check, okay, the type of method M's parameter is T, so with these rules we just assumed there was one parameter per method. So here that type is socket, and then we say, okay, for that type T, is there a method that must be called? So in this case, for sockets, we've modeled it as you have to call close on that parameter, and then here's where things become optimistic. We check, does there exist an invocation of that finalizer method, that resource releasing method within the body? We don't check, is it true that on every control flow path through this method is close called? We just check, did they try to call it? And if so, we go ahead and infer this owning annotation on the parameter. And I have a more detailed example, but that's in the bonus slides. So if we have time at the end, we'll get to that. But this is the basic idea of how the inference works. We've defined a bunch of rules. We handle owning fields, resource aliases, the must call annotation on types, and we run these rules to a fixed point. So let me show you some of the results. So first, we had a bunch of benchmarks that had been annotated by hand already. So a question is, how many of those annotations were recovered by our inference? I think the overall average across all these benchmarks was, between 75 and 80%. It's actually interesting how it breaks down. We looked at 3 proprietary C# services, and on those, we're actually able to infer 100% of the annotations that were written by hand. And then our numbers are kind of lower on these open source Java programs. And if I look at the causes, it's like sometimes there's a class that exposes multiple public methods that close a resource. And like the human being picked one based on reading the code that was the finalizer method, and our inference tool just picked the different one. It didn't know. There was another weird case where there was like an abstract class, and to understand which method was responsible for closing the resource, you had to look at the concrete subclasses, and we don't do that level of analysis. So I can't say there was like one quick fix to get this number up. There were just, sort of complex code patterns that our inference technique can't handle yet. But, overall, we were reasonably happy with these numbers. And then the next thing we wanted to look at was, what was the impact on the warnings emitted by the tool without running inference versus with running inference? So this is with no specifications. This column was without running inference. And this is with running inference. And you might think, oh, with the inferred annotations, I would expect the number of warnings to go down. But in many cases, it actually goes up, which is maybe kind of surprising. But then the reason is that we're actually discovering new wrapper types during inference, and that creates new obligations that must be satisfied, like new types that need to be closed. So here, if you go back to this MySQL connection, let's assume that we inferred all these annotations. Then after I do inference, the checker is now going to look at all the uses of this wrapper type and make sure that dispose is called on it. So it's actually interesting that, in certain cases, the number of warnings went up. We think that's due to finding a bunch of wrapper types that then need to have new things checked on them. And so finally, we kind of categorized the final set of warnings after inference. And first, we looked at the kind of the false positive rate. And it's, in the ballpark, at least for C#, of what we were getting without running inference, right? So this is pretty encouraging. The hope is that you're getting an almost equivalent false positive rate, but hopefully better warnings, because we've inferred a lot of the protocols that are being used to manage these resources. Very few warnings due to incorrect specifications. Like most of the specifications that we inferred were actually correct. There were cases where we missed specifications and that led to warnings. This is an area where I think we could improve. For C#, there's a lot of types that kind of implement the closable interface, but they don't actually manage resources. So there, manually, you can kind of specify, oh yeah, it implements closable, but this actually doesn't manage a resource. Our inference is unable to do that. So that led to false positives in C#. In Java, there are a lot of cases with owning fields that are mutable. And I didn't get into the details of this, but actually checking that those are managed correctly is more complicated than for a final field. And our inference doesn't do a great job yet with inferring all the necessary annotations to handle mutable fields that hold resources. In fact, that's one of the things that we're looking at in our ongoing work. So we're still pushing forward on this project. One thing we're looking at is resource leak repair. So actually, Akshay Ature and Jens Paulsberg published a really nice paper in the last FSE about automatically repairing resource leak issues, and they used our checker and were able to repair some of the issues coming out of it, but they didn't use the inference. So we're thinking that if we combine our checker and inference, and we're looking at some new fix patterns for these leaks, we might be able to do a better job of automatically repairing leaks in programs. So that's something we're actively pursuing. We generally want better handling of mutation, including arrays and collections. Remember I said this was one of the biggest causes of false positives. So this is hard. We're trying to take some inspiration from Rust and how it manages like arrays of resources and this kind of thing. But we've got to try to strike a balance here, right? We don't want to have you to annotate like every array manipulating code in your whole program. So this is still very much a work in progress. I don't think we have a good solution here. We're still thinking about it. We have other inference improvements that we're working on, and we're also thinking about applying this technique to other domains. So there's been a lot of work about structured concurrency and trying to not leak threads. We think that this tool could be helpful for detecting thread leaks. There's also been a lot of work on specification mining of the property that you always need to call this method on this type. And we want to look and see if we can integrate those mine specifications somehow with our tool and see if it works well for kind of verifying a bunch of extra properties that we didn't even define by combining with specification mining. So that's it. In conclusion, I talked about the resource leak checker. So with this insight that we can build the core verifier without doing whole program alias analysis, that we can do targeted alias tracking, we came up with a tool that I think is a genuinely kind of new trade-off in the design space. Like you need to write some annotations, but I think you can get much better confidence compared to other tools out there that you're really catching most of the potential leaks in your program. Then I talked about this resource leak inference technique. We use this optimistic inference to try to capture what we hope the developer intended rather than being super strict about it. And we had some pretty good results with that too in terms of finding manual annotations and getting a precision level that's similar to what you had without writing the annotations in the first place. So yeah, I'm happy to take more questions, and here are the links if you want to download either the Java or C# tools. So thank you very much.
Yeah, thanks for the talk, first of all. Just one question. I think you mentioned this, but I'm not quite sure. So there is a way to, for example, classes to contain multiple multiple sockets, for example, and without it being considered a resource aliasing, just normal containment, and this works. Okay, so there's really a different kind of special case for when it's an alias, but there's also the normal containment that's covered, and like.
Oh, right, so you're talking about a case where maybe I have 2 or 3 sockets that are managed by this wrapper class. So that's supported. Those can all be owning. It's just that it's no longer a resource alias with any of the individual sockets. So once you have that, our tool, well, you basically have to call the disposal method on the wrapper type now. I mean, I guess you can either do that or call it on all the sockets that you passed in, right? Because now you have multiple resources. So I think in that case, we'll basically, we can only verify it if you call close on the wrapper type. But we can still handle it. It's just not a resource alias anymore. So it's not a case where you can close this or that.
Very interesting. I wonder about the different results that you got for Java and C#. I wonder, is there anything fundamental the way these programming languages deal with resources that leads to the different results that you have? I think you had 2 positive cases on resource leaks, and there were apparently, I think, fewer in C# than there were in Java. I think it was this way around. Does this have something to do with the language, with the framework, or did you just miss more for one language?
It's a good question. To be completely honest, I don't think we have enough benchmarks really to make broad conclusions about like how programs are written in one language versus another. An issue that did crop up that definitely affects the checking algorithm is that C# does not have checked exceptions at all. So it becomes much harder to define a good heuristic for which exceptions to ignore and which method calls you should assume might throw an exception. Checked exceptions help a lot with that in Java. So that actually impacts like how the tool works. It's got, the RLC# has more heuristics in it. And that might have an impact on these results too. It's kind of not exactly the same checking algorithm because of the lack of checked exceptions in C#. So yeah.
So to put it bluntly, you're not saying please use C# instead of Java if you want to avoid resource leaks.
I would agree with that, yeah. Or if you're designing the next programming language, like I know checked exceptions are kind of a pain, but if you care about resource management, it's really helpful to kind of know that this method you're calling might throw an exception, like, and it's declared there, and you should really, as a caller, think about handling that. From the perspective of resource leaks, that's really important.
All right, so let's thank the speaker again. Okay, so our next speaker is Thomas Queller from INRIA, and he will be talking to us about interactive source-to-source optimizations validated using static resource analysis.
Thank you. So I'm going to talk about this work, which is also about a tool that we built around this called OptiTrust. And this is work that I've done with with my other colleagues from INRIA, and in particular, Arthur is here today. So first of all, what is our motivation for this work? Our motivation is that producing high-performance code is hard. So if a programmer wants to optimize their code, they have multiple options. Ideally, they would like to use some automatic optimization tools, so typically compiler. But compilers have a very difficult task in optimization. So they have to decide what optimizations are correct, and they also have to decide what optimizations are beneficial. So in practice, compilers often fall short. This is because they rely on fragile heuristics, or they have a restricted optimization purpose by design. So either a restricted domain of application, or the optimizations that they try to apply are limited. And the problem is that when compilers fall short, programmers typically fall back to manual optimization. So the problem with that is that manual optimization is time-consuming and error-prone. So we don't want that. We don't want programmers to have to choose between automatic optimization and manual optimization. This is why we care about interactive optimization, but there aren't that many interactive optimization tools out there. We want to save time with automation, avoid errors with static analysis, but at the same time, we still want to leverage human expertise and to avoid the fallback to manual optimization. So that's why we built the OptiTrust interactive optimization framework, where the overall idea is that users direct optimizations over C code, and the OptiTrust framework will check the correctness of the applied optimizations. So we are working on multiple case studies, and we have 2 case studies that are working right now. The first one is matrix multiplication in the domain of linear algebra. And this is the case study that I will focus on for this talk. But we also have a fully working case study on image processing, where we optimize box filter on rows, which is standard in bigger image processing pipelines. And we are also working towards more complicated case studies. So there is one in image processing called high-risk corner detection, and one in physics simulation that is called particle in cell. So focusing now on the matrix multiplication case study, if we think first about how you would optimize it by hand, this is what it would look like. So you start from naive C code, as you can see on the left, which simply is simply using 3 nested loops and a sum accumulator. And after a lot of trying out a lot of different ways to rewrite this code, you end up with the code that is shown on the right, and I don't expect you to read all the details. But the bottom line is that this code is 150 times faster on the CPU. It takes about 7 times more characters to write, and the entire manual optimization process is very time-consuming and error-prone. So it's common to spend months optimizing this kind of code. The optimizations that are applied at a high level, so the code is specializing input sizes here to constants of 1024. So these are the dimensions of the matrices. We're improving data locality by applying common loop transformations and also data layout transformations. And we're also parallelizing the code. So we're adding vectorization and multi-threading. If you don't want to do this by hand, the alternative in the state of the art is to use domain-specific compilers. So in TVM, for example, which is an industrial strength compiler for machine learning, you can describe what you want to compute on the left by writing what they call an algorithm. And you can separately write on the right side describe how to compute this algorithm by writing what they call a schedule. So I'm not going to go into the details of the syntax, but this approach has some advantages and inconvenience. So if we think about the algorithm description, what is nice is that this is a high-level domain-specific language, so it's concise to use and it's also easier to analyze than other languages. But the problem is that the domain of application of this language is restricted by design, and in particular for this matrix multiplication optimization, the algorithm had to be rewritten in order to apply optimizations, even though the promise of the separation between algorithm and schedule is that you shouldn't change your algorithm when you optimize it. But here, we had to rewrite it anyway. And then if you think about the advantages and disadvantages of the schedule on the right, schedules are fairly concise to write if you compare it to the final optimized code that is generated. And it's relatively safe to write as well, because at least in theory, TVM is promising us that we can write any schedule and we will still compute the same thing that we described in the algorithm. The problem with these schedules is that they have a limited set of built-in optimizations. So if you want to perform an optimization that TVM does not support, it can be very difficult. And also, TVM combines the algorithm and the schedule to generate some code using some black box that is very hard to understand. So for a given algorithm and a given schedule, there are many ways to generate code. So TVM uses implicit heuristics, and if you don't like what these heuristics are doing, you don't have control over them. And if you want to understand what is going wrong in the code generation process, it's difficult because all you have are intermediate representations of the compiler that are not meant for the user. So instead, what we do with OptiTrust is that we describe what to compute directly using general purpose code, so C code in this case, as shown on the left. So here you just find again the naive program with 3 loops. I just added a function signature around. And we describe how to optimize this code by writing what we call a transformation script. So when I say that we start from general purpose code, there is we do have to annotate this code because C code is very hard to reason about in general. So we ask the users to also add some resource annotations, and I will talk a little bit more about them in the following slides. But overall, with OptiTrust, we apply source-to-source transformations. So that means we don't have, for every intermediate optimization step or transformation step, we actually have C code, and our output is C code. We validate these transformations using a static resource analysis based on separation logic that I will talk a little bit more about. We don't have any black box code generation, because when you apply the transformation script, you just have you're transforming the C code, and in the end you just have the C code. So you don't need to apply any heuristics at the end. And it's easier to compose and to extend because if you have 2 transformations, you can put them back to back, and you can also add a new transformation without having to change any code generation process, like for TVM. So if we look a little closer at these annotations, the user needs to provide function contracts. So here we have clauses that describe ownership of resources, or you can also think about them as permissions. The reads clause is saying that this function is reading 2 matrices. So we're reading from matrix A, and we know its dimensions. And we're also reading from matrix B, and we know its dimensions. The modifies clause says that we are modifying matrix C, so we're at the same time going to read and write to matrix C. And when I say matrix, we see matrices as conjunctions, as a conjunction of cells. So for us, a matrix is just a bunch of cells, and we write it with these stars with ranges, as you can see on the bottom of the slide. The user also needs to provide us with partial loop contracts. So here we have these new clauses that are X modifies. And what's particular about them is that they describe resources that are exclusive to loop iteration. So here, these two annotations, overall, what they're saying is that the loops over I and j, they separately modify different cells of the matrix C. So we know that we're not going to have any dependencies between these iterations on this resource. Now we also automatically infer some more annotations. So without going through all of them, what's interesting is that we have also shared resources for loops. So we have, for example, the S reads, where S stands for shared, which means that these resources are shared among all iterations, and there could be dependencies between iterations on these resources. And we also insert what we call ghost operations. So you can see, for example, the matrix focus ghost operations. And these operations, they are just here to explain to our resource analysis how to change view on resources. So sometimes there are some reasoning steps that are difficult to automate, and these ghost operations are here to explicitly tell us you need to apply this reasoning step. Once we have all these annotations, we can automatically compute the resources available at every program point. So it looks somewhat like this. And without going over all of these resources, what I want to point out is that here in blue, we have this resource called named R1 that says that we own a fraction of the matrix A. So the fraction here is what we use to encode read-only resources. So if we only own a fraction of a resource, that means we cannot write to it, and we can only read from it. And we can look at another resource. So here, the resource 10 on the sum is not a fraction, so that means we can write to it. And in fact, we can see that after the for loop, the resource name has changed, and this is because we not only track what is in memory, so we don't only care about the fact that we have a cell at the address of sum, but we also care about the fact that this for loop has just modified this resource, so we changed its name, and we know that modification happened. Now if we move on to the transformations that we are applying, most of the transformations from the scripts are what we call combined transformations, which means that they are composing basic transformations, and they are valid by composition because we ask basic transformations to check for correctness. So in our MATMIL case study, we have 8 script steps that result in about 55 basic transformations and also 61 ghost transformations. So these are transformations that are purely that are only here to help with resource computation. So if we look at the first transformation step, even though we are just specifying a loop order that we care about, behind the scenes this is achieved by applying 18 basic transformations, and in particular transformations that swap or fission loops. We can visualize, because OptiTrust is an interactive tool, we can visualize what the script is doing. So this is a screenshot of what the user can see with, on the left, all the transformation steps that are applied with the substeps, because we have these combined transformations that call over transformations, and in the middle, difference. So you have the code before the transformation step that is currently being visualized, and the code after the transformation. Regarding basic transformations, they directly transform the AST. And so internally, we don't directly work with CAST. We transform a simplified imperative lambda calculus. And each basic transformation is responsible for checking sufficient correctness conditions. So we have transformations on instructions, functions, variables, etc. Just to give an idea of what our correctness criteria look like, this one is for moving instructions. So we need to know when it's safe to swap two groups of instructions. And without explaining the formalism that is on this slide, what is important is that we are leveraging the computed resource information. Here that is, you can see with the delta 1 and delta 2 that tell us how these group of instructions are using our resources. And intuitively, this is correct if the resources used by T1 and T2 are exclusively shared in read-only. We can also have more complex criteria for loop transformations, so loop fusion here, for example. And I don't have time to explain how this criteria works, but what is interesting is that now you can see with this key variables that we're also leveraging the loop contracts, and that we also have to synthesize on the right side a new loop contract, and we can do this. So to conclude, OptiTrust is an interactive framework for optimizing general purpose C code. Transformations are validated using a static resource analysis. We've completed 2 case studies. We are working on more, and we're interested in hearing if you have other case studies in mind. We have a lot of future work on mind as well. So thank you for your attention. We are open to collaboration, and you can also find our code online, which is open source. And you can also play around with the traces of our case studies if you want to see what is happening in more detail.
We have time for a couple of questions.
So one optimization that matrix multiplication is usually using is a loop interchanged. So you switch the 2 inner loops. Is that an option that you can support here, or this is beyond what the tool can?
Yes, that's just what is called loop swap here. So this loop reorder at is doing 4 loop interchanges.
Mm-hmm. Thanks.
Hi, this is really interesting. Can you say a little bit more about what exactly is computed by the static resource analysis? I think what's going on is that it computes something like the memory footprints for each instruction, and then you use that information along with extra conditions to verify the correctness of these transformations. Does that sound right?
So we can see it a little bit as type checking, and what we have is a typing context at every program point. So what I've shown here between the instructions, and this tells you what are all the available resources, and also, for example, whether you only have a fraction of them. And you can also know, if you compare the context before and after an instruction, you can know what if the instruction has changed any resource. So that's what we're computing.
Right. And then you need to check some extra conditions on top of that to show that it's like an input to the, it's information that's available for the correctness checks.
Yes,
like on its own, it doesn't
every transformation, so on its own, it just says the code is modifying this, using these resources in a legal way. But then each transformation has their own criteria. So like this one, where they leverage this information, but they have to individually check for their own conditions.
Thank you.
Yeah, just as a follow-up question, as a sanity check, Initially, I think you showed some hand-optimized version of the matrix multiplication or something. Is it possible to get to that state with your tool, or is that beyond
yes,
what you can do right now?
That's exactly the tool that the code that we are generating. Maybe I should have made that clear.
Okay, thanks.
Thank you. That was exactly my question. Okay, one more question.
Sorry, I came in the middle of the presentation, and I'm a bit puzzled with the annotations that you are requiring that be made, because it seems that several of those properties could be identified by static analysis without needing for annotation.
I think if you have tools that can infer these annotations, it's something that we would always like to automate more. But I think we're coming from more from the side of the manual optimization, in the sense that we want to be as expressive as possible without having to worry about what can be automatically inferred and what needs to be annotated by the user. And then as a second step, do things like I've shown on this slide, where we automatically infer some of the annotations, and of course, automatically inferring more of them is always beneficial to us.
Okay, my view might be biased because we work in matrix multiplication quite a bit, and we did pattern detection of those things. So,
thank you. Let's take the speaker again. Thank you. Okay, and our last speaker for this session is Julian Erard from the Technical University of Munich, who's going to talk about when to stop going down the rabbit hole, timing context sensitivity on the fly.
Thank you very much. So this is joint work with Johanna Schinderbeck, Michael Schwarz, and Helmut Seidel. And I would like to start with a motivating example. So here you can see a very simple recursive program with some main function that calls some recursive function f that calls itself with a decremented parameter. And this will go for a while and call itself 100 times. And now let's assume that we want to analyze this program with a context-sensitive static analysis that uses, for example, an interval abstraction. So how would we go on to do that? So at first we would start from the function main, and we would have to look at the function call that is happening there. And for that, to analyze this function call, we would analyze the function f in the context where x, the parameter, is 100. And now, of course, we would again have to analyze the function call that is happening within this function invocation. And we would have to look at the function f in the context where x has the value 99. And again, we would have to look at another function call, this time in the context where x has the value 98. And this would go on for quite a while until we enter the rabbit hole, so to say, and hopefully come back. So in this case, there will be an end, and when x reaches the value 0, we will be able to come back. But there will be recursive programs for which this will not terminate, and we will continue to look on further and further contexts. And that may even be the case when your recursive program always terminates, because you have some over-approximation that leads you to look at more and more contexts. And so if you come back from this rabbit hole, then maybe then you can compute the states after the calls of all these functions. Okay, so that's certainly something that in some circumstances we want to avoid, and we want to have some trade-off between analyzing everything context sensitively and ensuring that we terminate. So what is our goal? Our goal is to limit the context sensitivity dynamically so that we are able to deal with recursion while still in general being context sensitive. And we don't want to touch all our existing analysis implementations, but instead reuse them as is. And additionally, we would like to avoid having to do some pre-analysis. So because a pre-analysis may often be imprecise or be costly. So what I just want to highlight some related work. There has been lots of work on how to tune context-sensitive analysis, but I just want to highlight something that is called selective context sensitivity, which follows the principle that you perform some pre-analysis, and then judging from this pre-analysis, you decide the level of context sensitivity that you apply in different places and for different functions. And for example, you may perform some pre-analysis that computes a call graph, and based on that, you decide that you analyze all functions that appear in any cycles that happen in the call graph context insensitively. But these approaches, they rely on pre-analysis, and here we want to present some approaches that do not rely on any such pre-analysis. So we propose 3 such approaches that allow us to tame context sensitivity, and they are called context widening, loop recall string, and context guess. And to avoid to change existing analysis implementations, we implement them as decorators or as wrappers around existing analyses. So to be able to understand how such a wrapper would work, let's have a quick look at how an analysis is defined. And so clearly for an abstract interpretation-based analysis, we need some abstract domain. We need, for context-sensitive analysis, we need some set of contexts. That is the set of contexts according to which we distinguish function calls, and some abstract semantics for program actions. And as we are interested in function calls, we demand that the way that the callee start state is computed, as well as the context, is clearly defined in the existing analysis. So we will call this function enter that does this, and to go with that, there will be some function combine that from the end state of the called function and the preceding state of the caller will compute the new caller state. And now let's quickly visualize that. So assume we have in the context C some function call at this edge here. We will first, using the function enter, compute the start state of the called function, and we will compute some context CF compute some context CF. Then, as usual, we will analyze the function and come up with some state at the end of this function. Then, using the function combine, we can take the state at the end of this function f in this particular context, together with the preceding state of the caller, and compute the new state, caller state. And so what our analysis lifters or analysis decorators have to do in particular is that they will have to define this enter function appropriately, potentially using the enter function of the underlying analysis. And now I want to quickly talk about context widening. So this is the first approach that we propose. And the idea here is that we use the widening operator that is already given by the domain to limit the number of contexts that are encountered when we analyze recursive procedures. And you will find more on that in the paper. And the next approach is called the loop-free call string, where we abstract call strings by representing cycles that occur in a call string by sets of the involved procedures. So, yeah, so this is some abstraction of the call string approach that gets rid of these cycles. And now I want to talk about the context gas. And the idea here is that we add some counter value, some gas, as part of the abstract state of the domain. And whenever we encounter a function call, we decrement this gas value and pass this decremented value to the callee. And in case the gas value has ran out, we use some fixed element out of this context, some bullet context as the context. So this ensures that whenever the gas has run out, that we use the same context, and all calls with zero context gas are analyzed in the same context. And so now let's have a look at the example again. We assume that we analyze the same program from before, now with some initial context gas of 3. And now we will have a look at the first function call. And there we will pass now the context gas, which is decremented compared to the caller state. So we pass a context gas of 2. And for the next call, we pass a context gas of 1. And now, for this call that happens here, we are in the situation that our context gas has ran out. And at this place, we actually now decide, okay, we do not use a context that contains all the information that we have usually, but instead we just use some bullet context. And now that ensures that when we here perform or analyze the next function call within this function f in the context bullet, that we actually will reuse the same context again, because the gas again has already run out. And here, so the first we will, in this case, have reached this node again with the value of 97 for x. And then our fixed point algorithm will then actually perform widening so that we can then compute a solution for this function invocation. And then based on that, we can compute abstractions for the states of the other, after the other function invocations that we have seen. Now, how does this turn out? And so we have made some experiments on SVCOM tasks, and I want to in particular highlight some experiments on a set of recursive SVCOM tasks that you can see here. So here you can see the full contexts as were shown in the initial example, and the call strings of unbounded length. And you can here see our 5 configurations with the loop-free call string, the context widening, and 3 configurations of context gas with different initial gas values. And so all these approaches were implemented in Goblin. And alongside with a completely context-insensitive analysis, as well as a 2 call string and a 10 call string analysis that we have here for comparison. And what you can see here is the number of correct verdicts on these tasks. So these were about the no overflow property, so whether we could show for a task that it contained no integer overflow. So these were all very integer heavy programs. So yes, so that was the task. And so with the green bars, you can see the number of correct verdicts that each configuration produced. And in red, you see the number of stack overflows or timeouts that were produced. So you can clearly see that for the full context and unbounded call string, you get lots of stack overflows or timeouts. So almost half of the task resulted in such a resource exhaustion. And now for our approaches, for the loop-free call string and the context widening, you can see that we do not have any such stack overflows or timeouts. And then unfortunately, the precision decreases compared to the full context approach. Now for the context gas, you can see that actually we get quite good results regarding the precision. And this is, for the higher context gas, you get actually better values with regards to solved tasks compared to the full context analysis. Unfortunately, for higher context gas values, you also get some stack overflows or timeouts. Okay. And so in this case, on this set of benchmarks, this context gas of 30 yielded the best results and better results in the full context analysis. Now, to conclude, we have proposed 3 means to tame context sensitivity, context widening, loop-free call string, and context gas, and they are implemented as decorators for existing analysis so that you do not have to adapt your existing analysis code. And these approaches manage to reduce the number of timeouts and stack overflows of recursive tasks. And albeit the precision for the loop-free call string and the context widening was decreased, we see promising results, in particular for the context gas, with regard to the precision performance trade-off and more solved tasks than a full context analysis. So that's it. So thank you.
Thanks a lot. Very interesting work. I was wondering, particularly for the loop-free call string representation, why does that lose any precision? Isn't that an equivalent representation of what you would normally have?
Compared to what do you mean?
I mean, normally, I guess you would have, just a repetitive occurrence of that function in a rather lengthy call string, right?
Well, no, there may be. So there may be, so it's not ensured that the cycle is always of the same form.
I see what you did. Okay, there's work, I'm not sure if you're aware of it, on push-down systems that actually model these context strings also. Well, they basically have loops in their representation, but that's more precise than what you have. So if you haven't looked into this yet, I would recommend that you have a look.
Okay, yeah, so we have, there's lots of work, as I said, on different, on all of these context sensitivity. And yeah, there are some other approaches on how to handle these call strings also, yes.
All right, thanks.
Thank you.
So we've looked into something similar, not for call strings, but for access path in taint analysis, where you have the problem with doubly linked lists, for example, that you're always going pref, next, and you're always returning to the same object. And if you put them together in a simple way where you just say, oh, I seem to be repeating myself, then you could actually generate false positives on that one, because you don't see when someone is kind of FG next versus just F next, because then you might also kind of stop in the middle. There are some of these corner cases. Have you experienced cases in which you lost precision due to that?
With regard to what approach? Or
with these loop-free call strings,
Okay.
where you're cutting things out that look like a loop, but they are not actually loops, which is not the problem of the concept, but of the detection when you should consider things a loop and when not.
So I mean, we have not looked too much into detail for the actual for the single tasks that were not solved anymore. So I cannot really report on that. But yeah, I mean, clearly the issue is that you just the amount of context that is distinguished is too small with regard to that approach to really obtain good precision.
Thank you.
Hi, cool talk. Can you go back to the results slide?
Yeah.
So the context gas goes up to 30, but the call strings stop at 10. So I was curious what happens if you set the call strings to 30?
Okay, so we have not actually tried that on that here, but we have made, so this is just a subset of the experiments, and we also tried some larger benchmarks, and we see that the 10 call string already tends to perform worse on larger benchmarks, so it has larger runtimes, and so the issue
Worse than the 30 gas?
Yes, so
Okay.
the thing is that due to the call strings, you distinguish more. You distinguish on the call strings, and so our analysis are not really, or mostly not interested in the call string, but on the abstract state. And so you introduce some artificial distinction between abstract states or between contexts that is not really useful for the analysis.
Okay, a quick follow-up on that. If I reach a function with the same abstract state from two different paths, except
Yes.
the gas is different, do I
Yes.
analyze it twice or once?
So that depends. So usually you would reach it with a lower value the second time, or a value that is as high, and in that case you would not reanalyze it again, because the way we have defined the ordering on the abstract state is such that on a join the higher gas value is maintained. And so if you come back the second time, the higher value that was reached, that has reached the first, is maintained. So you do not have to reanalyze it. So that's a nice twist. But of course, in the rare circumstance that the second time that your fixed point solver comes there and you have a higher gas and the second time, then it may increase actually, yes, and you would have to compute.
Okay, last question.
So I'm wondering, so what is the difference between the context gas and conceptually just unrolling the recursive call? Is there any difference?
So the point is that we don't give up on when the context gas has run out, but we just, well, it depends on, well, so you do still a context insensitive analysis, and actually you join all the calls together from everywhere that reach this function with context gas 0.
So one question also about this context gas idea. So does this mean with this technique that the result of the analysis suddenly depends on the order that the analyzer chooses to visit the different parts of the program? So it may run out of gas differently depending on basically the work list order or something like that. So you end up having like a non-deterministic result of the analysis.
I think that should. I think that should not be the case. So we actually, I have not given it. I have not considered that in very much detail yet, but I think so. The gas value should always be computable by the shortest path with which you can reach this abstract state or with which you reach the function invocation.
There's time here. Okay, so let's say you have like an if-else branch, and then you have calls in both the then branch and the else branch, and then decide, depending on which order you visit the then and the else branch, then maybe you run out of gas while looking in the then branch before you get to the else branch, all the way around.
So within a function, you maintain the same context gas value. So it's only for the called function that you decrease the context gas value. So it will.
Yeah, maybe let's take it offline. So yeah, time for the break. Okay, well, let's thank thanks the speaker. Let's thank the speaker again. So we'll come back to our last session at 4 p.m.
So, welcome everybody to this afternoon session. I am Helmut Seidel from TU München, and I will chair this session. Our first presentation is about misconceptions about loops in C. So, please go ahead.
Hi, I'm Martin. I don't really know what loops are. This is Maddie. He does. I'll talk to him afterwards. all entry edges go to the same location. So this is on entering. All entry edges go to the same location. Seems fairly reasonable. Oh, what the hell is this? This, of course, is Duff's device. If you haven't come across this, this is a technique that was proposed by Tom Duff for realizing that switch just have to go to labels. There's nothing to stop you hiding a loop inside your switch, at which point where you jump to in the loop depends on your variable. And it's really handy if what you want is your compiler to optimize those 4 and do them as a block, but also not have to do a separate loop where you do 1 to 3 of them. So it's really compact, produces really nice code if you're a 1980s compiler, and it's very much still out there in the world. What's not as widely known, though, is there are worse versions. Duff's device is not as bad as this gets, right? There's an amazing paper, we cite it and I've forgotten the author. Somebody says, hey, you realize you can build reentrant state machines like this in C. It's fine, just use these macros. And they're using this trick. It's horrendous. It's in putty. So if you've SSH'd in from Windows, you've used this. Another one. Do we want another myth? I don't know. How much time have we got? 10 minutes. Okay, we definitely want another myth then. Somebody else had their hand up further back. Which, at the end of a loop, so this will be under exiting. Oh, inside. The end of a loop is an unconditional jump, right? This is very much the kind of thing that we said we're teaching people. Okay, well, let's see if it's true. The end of a loop is an unconditional jump. No. No, it's not, because do while loops, you might wind up with a conditional jump at the end. Okay, now is this the one that I'm like, you can fix this with one unrolling? I can't remember. No, it's not. So yeah, this one, you might wind up with your last instruction being conditional jump. So, what else? What other myths do you think your students might fall for? Not that I'm giving you exam questions or anything.
Back edges are the same as backwards jumps.
Oh,
I
I love this one. We actually had a genuine bug report on this. God knows what they were doing to make it happen. Second to last. Definitions. Oh, definitions, my bad. Oops. So, if your code is compiled up, if you're using the list of instructions representation, and you're like, oh, it's fine, we can find loops because they've got back jumps, then, and some idiot writes this. So, go to A, go to B, go to C, then you're clearly going to have a backwards jump. But of course, when you feed it into a control flow graph, whoom, like that, like the magician, it all just straightens straight out. Simple, right? Oh, and we've lost our back, so I have to go back. Okay, any more? Should we do some more? What other myths are there? I'm going to pick him because he hasn't asked one yet. Oh, I love this one. Again, almost all of these, like at some point, me or somebody I'm working with has screwed up. And this one, oh, it took so long realizing what the hell was going on. Inlining is harmless, right? You might inline for performance. You might inline just so you don't have to do context-dependent analysis. You might inline something like this. So we've got a function, nested loops, we return out of the nested loops and at the end. Reasonable, well-behaved code-ish. Doesn't involve any go-tos. Now, when you inline that, if you're not careful, you may wind up with something you can only express with a goto. Because if you inline this code into another loop, what you will wind up with are exits from inside, not just out of one, but out of several loops, and into an outer loop. We found this one by like scanning this, looking at the source examples. They're all well behaved. There are no go-tos here. Like going back through all of the the handling of the control flow graph. Where the hell are the go-tos coming from? Turns out the answer's in lining. I'm going to be cheeky and pick the next one because like I like continuing this theme. Gets me. I can tell a joke. So it gets more fun though if you implement jump threading. I tried to look this up whether it has an official name, but this is the optimization where if you're a go-to or any kind of conditional control flow and your target is an unconditional go-to, then you might as well just shortcut, right? Harmless operation, right? Couldn't possibly screw things up. So if you take the previous one and you inline it and then do jump threading, then what you've got is a jump from anywhere in the body of this function to here, or likewise to here. Now, this is not quite an uncontrolled go-to, but it's almost there in terms of the level of chaos that you can generate. So this led to me saying that I feel like both breaks and returns are like domesticated go-tos, but breaks are domesticated in the same way dogs are domesticated, and returns are domesticated in the same way that cats are domesticated. So, anyway, Chair, how much time have we got? I should stop this now. 5 minutes. Okay, should we do one more then? One more. If you want any of the others, then you're going to have to read the paper, I'm afraid. Or you can ask Maddie, because he knows them all. One more? Loop. Oh, okay, well, this is quick. Not all loops have contents. So if you want to busy wait, you can often wind up with a loop that just doesn't have anything in it, and this is a perfectly legitimate thing to find in your code. But of course, if you've got a API function which says return me the body of the loop, then if one made a mistake like that, then you'd ship code out and you'd find it crashing at some point with a null pointer exception and no obvious answer as to why, because like clearly there's got to be something in the loop, right? I'm going to pick one more just because I like the amount of chaos that it can bring. So you start out by a simplification. Oh, but it's fine. It only removes edges. Doesn't change the number of loops you have. How about this? So we've got a macro that just tests whether a pointer is read-write. And we've got a pair of nested loops. So we've got 3 loops. Right? Or do we? Because maybe actually you're doing this slightly later on and you've already got rid of this. So maybe we've only got 2 loops. But maybe actually you already know something about P. Maybe it's a pointer to a local variable. So you know that this will always be side effect free. So it's fine, you can optimize it away. It doesn't do anything. Now at this point, if you remember back to your definition of natural loops, you'll find that you've got 2 natural loops, but they share the same head. So the only sane solution is to treat them as one loop. So, depending on how much you know about P and where in your optimization process you do this, this is either 1, 2, or possibly 3 loops. Right, I really should stop this. So conclusions. We came up with 4 recommendations, which is that if you're designing APIs for working with loops, design for the general case. Design so that your API function is not give me the loop entry point. It's give me the entry points. And then maybe you have a separate separate function for, is this a single entry loop? But always design for the more general case, because it's really hard to go back and undo that. Secondly, put preconditions in. It is totally morally acceptable and fine to go, we are not going to handle some of the horrible, horrible cases, but you should check that. You should put a precondition in, and you should give a meaningful error message, because trust me, later on when your tool becomes popular, people start submitting insane bug reports. Yeah. Also, if you have multiple uses of loops, if there are several points in your code where you touch loops, like, you know, early on you look at instrumentation and then later on you're doing, I know, loop acceleration, expect that you'll have to track between them. Because as we show, loops can vanish, merge, appear from nothing. Yeah, just the, oh, it's fine, we did loop analysis back there, that'll still hold here. Not true. Last one, systematic test cases. So definitely talk to Maddie about this. We have a collection of the horrors that are in the paper as useful standalone test cases, which hopefully have assertion failures when you miss a path. We are actively trying to distribute them. If you have any other horrors that we've missed, please do let us know. Anyway, thank you very much for your time and attention. You've been incredibly patient. And I think that's all.
Thank you. Thank you very much. Other questions?
Thank you very much. I was wondering about the distribution, if you plan to submit it to like something like the software verification competition or NIST tests or something.
I've thought about submitting it to SV Comp, but I don't know whether they'll let me into the building again afterwards. Like just trying to run these through CBMC, which doesn't necessarily do any particularly fancy loop analysis. We've found not only some like really exciting weirdnesses, we've also found horrible things like, well, this is clearly showing exponential behavior, but we have no idea why. So yes, I think we should. I'd quite like to, but I don't know whether anyone will ever speak to me again if I do, because some of these are horrible.
I think some other people submitted some horrible stuff, and that's part of the competition.
I had a small hand in some of the floating point stuff, so yeah, okay, and people still talk to me. Fair.
So one more question.
Great talk. I think the obvious question is, how many loops do you have in your slides?
Oh, Jesus. Before we started, afterwards?
Internally and internally and externally.
Oh, Jesus. I mean, do you count the hyperlinks? You know, do these count as loops? In which case, I think it's about 17 or something.
I guess it's one strongly connected component, maximal strongly connected component.
I hope so, but like, I mean, there are some hidden slides at the end that you have to ask me about if you want to see them. So I don't know if they're connected. I'm sorry, I don't know the answer.
Okay, thank you very much. So, and our next speaker is Joanna, and she will speak about a better approximation for interleaved dike reachability.
Hi everyone. My name is Giovanna, and I'm going to be presenting a better approximation for interleaved dike reachability, which is a work I did with Andreas Plavayanis. So first of all, let's talk about what interleaved dike reachability is and why do we care about it for static analysis. And here we're going to be trying to solve a very simple problem, which is if the value of a variable A can flow into another variable C in a program. That's very simple. You can imagine all the applications that this can have in all these different types of static analysis. We're going to be focusing on like one specific set of benchmarks here just to exemplify our tests. And we're going to be testing on a taint analysis benchmark on Android. So essentially seeing if you taint a variable. So if there's a flow from some sensitive data, such as your phone's location, to somewhere you don't want it to be, like an untrusted sync, a log to an app that might be malicious. So how do we solve a problem of if a variable can flow into another one? If we look at this little program here, right? An intuitive thing is to create a graph. So we add an edge between two variables. So here A goes into B. We add an edge from A to B. And now we only need to check if A reaches C. If A reaches C, then the value of A goes to the value of C. And this is very cool, but it kind of gets a little bit more messy once we have more complex programs. If we have function calls, so let's say something like this, right? And we have that the value of A flows into B, because A goes into this next. Next X is going to be next A, return A plus 1 goes into B. But if we do the graph here, like we described before, well, A reaches B, which is nice, but also C reaches B, because C goes into next. We have next of C, return C plus 1, and we have the return here. And we don't want to identify these types of paths. So one way to deal with this is to put parentheses. So whenever we call a function, we add a parenthesis corresponding to the call site. And when we return, we must return where we came from. And now all the valid paths here are well-nested paths in parentheses. So like A from B is well-nested, but C from B is not well-nested anymore because the labels of the parentheses don't match. And we have a similar thing when we're talking about compositive data types. So here, for example, I have that A flows into the X field of P, and then the X field of P goes into C, so A reaches C. But through the Y field of P, B also reaches C. And we need to handle this using this time brackets, so we differentiate them. And the path needs to be well nested for us to have a valid relation here. Awesome. What about if we have, oh, okay. So how do we check if a path is well nested, actually? Well, well nested parentheses is what we call a DIC language, which is a context-free language, which means it can be written this way. And when we're talking about finding all the pairs in a graph that have a path that belongs to a certain context-free language, this we can do in O of n squared, and this is good for us. Let's be happy about it. Okay, but now what if we want to handle both context and field sensitivity simultaneously? Things get a little bit hairy here. So we have this program that has both. And I'm not going to go into this example very much, but essentially we want to find a path here from A to C that looks something like this. If I take this path and I write the labels, and I squint, and I only look at the parentheses, this is well nested. And if I squint another way, and I only look at the brackets, that's also well nested. So this language is called interleaved DIC language, which is the interleaving of two DIC languages. And finding interleaved reachability is actually undecidable. So we cannot solve this problem ever. There's no algorithm. There never will be. So let's seek to over-approximate the number of reachable pairs. First of all, I'm going to talk about some current approaches, and then I'm going to talk about how we improved on them. The first thing you may think of is intersection. I said that if we squint one way and you only see parentheses, it should be valid. And if we only see brackets, it should be valid. So let's do this. If I want to see if A reaches I, I'm going to check if there's a path valid from A to I in parentheses, ignoring all brackets, and a path that's valid, ignoring all parentheses. If it's valid on both, then I say that A reaches I, and I'm happy. Of course, this doesn't solve the problem because it can't. So we can have a problem like this, right? Here, the path from A to E that's valid on parentheses is different than the path from A to E that's valid on brackets. But our algorithm is going to say that A reaches E, even though there's no path that is reachable on both at the same time. So what we're going to do here is we're going to run these algorithms, and each of them is going to present us with an over-approximation, and I'm going to be plotting the number of potential false positives. It's potential because I'm comparing it with under-approximation because we don't have the exact number, because undecidable. So this is what it's going to look like. I have all these benchmarks, and these are the potential false positives normalized by worst method. Why are they all the same length? It's because this is always the worst method. Out of the methods we're going to compare. It's kind of the naive approach. Then now let's talk about our first real algorithm, which is the mutual refinement, which was proposed by Schrödinger and Kirun-Zhang last year. And this works by iteratively simplifying the graph. If we look at this graph here, we have this closed parenthesis 3. But we don't have an open parenthesis 3. This means that this edge is never going to be part of a valid path, right? So we can just remove it from the graph. So we're going to essentially be doing this with both languages. We identify all the paths that are reachable through parentheses, and we eliminate the edges that are not in any of them. And we do the same for brackets. And now we get a new graph that has less edges. And then we do this again. And we do it until the graph that we start with is the same as the graph that we end with, i.e. it converges. In practice, this generally converges pretty fast. So it converges like in around 3 to 5 iterations. And then once we converge, we run intersection on this final graph. Notice that this method is also not perfect. Let's look at this example here. The path from A to D is still misidentified. Here I don't remove any edges because these edges here on this upper path are all in a valid path from A to E, and the one in the lower are all in a valid path from A to H. But there's no valid path from A to D. But how does it perform compared to our previous intersection method? It's a significant improvement. Maybe like half the paths here, half the potential false positives. So it's a decent improvement. Let's see how we can make that even better. The first thing we may think of is augmenting this context-free language, because we're essentially running two languages. One of them, we only look at the parentheses and we ignore the brackets, and the other one, we only look at the brackets and we ignore the parentheses. But this is wasting information. We could essentially add some information to the brackets that's easy to incorporate into a context-free language, and that would make the languages we're considering more refined. So let's look at this previous example of mutual refinement and try to come up with a reason on why A will never reach D. Kind of an easy excuse that we could just incorporate into a CFL. And an easy property of these DIC languages we can exploit is that they're always even. When we add parentheses, we're adding 2 of them at a time. Since these paths all have odd length, they're never going to be valid interleaved DIC paths, right? So we can just now, instead of our CFL identifying strings that the parentheses are well nested, we're going to identify strings that the parentheses are well nested and the number of bracket characters is even. And then we're going to run mutual refinement for this grammar and the bracket equivalent in which the brackets are well nested and the number of parentheses is even. Another thing we can do here in augmenting our CFL, let's look at this example now. This is an example where all the conditions I said so far fail. So our algorithm would say that B reaches D, even though it clearly doesn't. And an easy condition on why it clearly doesn't is because all the paths from B to D start with an open parenthesis or an open bracket. And when you think about a well-nested parenthesis, it always starts with an open parenthesis or open brackets, right? So we're going to augment our CFL again, and now add a condition for the parentheses that the first bracket must be an open bracket, and the last bracket must be a closed bracket, and vice versa for the bracket language. And we're going to run mutual refinement on this. These are all conditions that are pretty easy to add to our CFL. And how does this perform compared to our previous algorithms? Well, we remove another bunch of paths. You see, for many of them, we're extremely close to our under approximation. And the last thing here we're going to be doing as an optimization is considering an on-demand setting. So let's look at this example here. Why do we not remove the bad edges from A to D? Well, because they are in a valid path from A to H, for example, or A to E. So if we only think about the edges and how they impact a valid path from A to D, then we would remove this open parenthesis here and this open bracket here. So we can run on demand for A to D if we really care about knowing if A tends D or something like that. So we're going to query for a single potential reachable pairs. And then we use mutual refinement and exclude edges that are not in a path from the exact path that we're asking about. And how does this perform? Well, we can decrease a reasonable amount of more paths here around. So now let's talk about some additional considerations and what do we get from all this. First of all, runtime, which is something that you guys are probably asking about. So our grammar augmented methods, they increase the CFL by a constant size. So it's going to be slower by a constant factor. And these grammars that we wrote, they're actually incremental, so you can choose to improve as many of the conditions as you want, and we actually have a generalization on one of these conditions. So essentially, for as much as you want, you can pay slowness and get like less reachable pairs. And the on-demand setting here, it increases precision if you're only talking about one pair. But of course, if I want to find all reachable pairs, I would have to run for all pairs. Not really, we can optimize that. But still, for all pairs, it's going to be much slower. But if I only want to know for one pair, it's going to be a little bit faster. So our overall results, essentially we designed stronger methods for over-approximating this interleaved dick reachability that improved on the previous best methods. And the number of potential false positives, which was purely 55%. So out of the pairs that are reported, only these we know are actually reachable, and these ones we're not sure. Now it's going to be 12%. So we know that only these are the pairs that we don't know. And actually, kind of off the record, we know that these numbers are actually much better. We are working on better under approximations, and we know that for these benchmarks that are showed, for at least half of them, we obtain an optimal answer, which means that for these benchmarks, we have the exact solution for this undecidable problem. But that's pretty much it. Thank you.
Thank you very much for your presentation. Are there questions? That's the first one.
Thanks, this looks super interesting. I was wondering, I'm not sure if I understood this right, but at some places it seemed to me that you would need to know already large parts of the graph ahead of time in order to determine what can be eliminated or not. Is that the case, or can you really do this all on the fly as you compute the graph?
No, we're doing like a static analysis, so we're kind of just getting the whole graph, the whole programmatic as an input. So we get this whole thing as an input.
But that's not normally how people do things? Okay.
Sorry. Yes.
Yeah. I mean, that can sometimes be prohibitively expensive, right, if you want to build that up front.
Yeah. So I know at least for this Android benchmark, we're looking into like vulnerabilities. So they were trying to look like vulnerabilities in programs that execute certain simulations. So it would be something about, this method would be used to detect like big vulnerabilities on code. So you could justify like running a static analysis, and in practice this runs like in a couple of minutes. So it wouldn't be something that you were gonna be running on your house whenever you code something, but more like a process to detect vulnerabilities.
All right, thanks.
You mentioned that one of the filtering methods is to check whether the length of paths is even. Could you also do that by checking that the length is checking the length modulo the number of interleaved languages?
What do you mean? Oh yeah,
So,
you mean to generalize this for like more parentheses? Or
yeah, so if you have, I don't know, say 3 languages that are interleaved, it's still true that it has to be even.
Yeah.
But would it also have to be a multiple of 3, for example?
No, because I could always like add 2 of just parentheses, right? They don't have to have the same length. I could have like, 5 pairs of parentheses and 0 pairs of brackets, 6 pairs of parentheses and 1 pair of brackets. So the languages are kind of independent. They each have to be even simultaneously, and the addition of 3 even numbers, the only guarantee we have that is even. But we do, like, in actuality, we implement a slightly more general version of this in which we check the parity for like subsets of bracket types. So we can say, for example, that like the brackets of label 1, those have to be even, and if we only look at the brackets of label 2 or more, those also have to be even. And we can keep like the conditions for each of those subsets in our grammar.
Okay, thank you.
So coming back to Eric's question, there has been a lot of work on trying to scale static data flow analysis, especially for Android apps. And there are many papers out there that talk about the memory consumption of that. And we're talking about graphs that even if you prune unreachable call sites, so you have a call strings approach when you return to something that is an infeasible call leaf, or that you just drop it, you don't even put it in the graph. We're talking about graphs of 30 gigabytes or more. So we're not talking about such small graphs. So I really wonder whether it is feasible for large apps, and we're talking about things like the Facebook app, we're talking about the large banking apps and so on, to really make this an analysis once you have the full graph. Because as I said, there are many, many papers complaining about tens of gigabytes of those graphs, even if you prune early on and prune eager.
Yes, Absolutely. Like, this is not gonna be able to run on something that is that large. The static analysis is already a compromise because running dynamic analyses on these types of applications is not feasible just because they are so large. And these methods, I mean, we're running here for like reasonably big applications, but I don't think they're necessarily scalable for something that's very huge, unless you let it run for like a very long time, which maybe if you're looking at like vulnerabilities for something as big as Facebook, they can afford the processing power or the size for it. But like, it's not, I think the point here was mostly to check like how good the over approximations are and try to find like, where are these numbers? Because we know now that like these previous methods over-report a large number of paths, and we know how to get close to them. But I don't think something like this will be running on the back end of any companies very soon.
Okay. So any more questions? If not, then thank you again. So, and we proceed with our next talk, which is about benchmarking exact value analysis. Oh, I think you took mine.
Yeah, I don't know which one is yours.
Let me test this. Okay, then.
Sorry.
This should be mine. Okay, after this small security incident, let's start with this presentation. This is about benchmarking exact value analyses. So I can skip over the agenda very quickly because you'll see this during the talk. This work has mainly been done by Mark Miltenberger, who is one of the PhD students in my department. So all the fame goes to him actually, but unfortunately he cannot be here today, so it is my duty to present this work. Now, before we talk about value analysis too much, we should first understand what a value analysis is. You see this piece of code, and since we're security people, we often want to find out whether there is a vulnerability in it. So we ask questions like, you initialize a secret key spec, so there is a cryptographic key going into this. Is this something that is hard-coded? So we ask the value analysis, give us the concrete value, and if it statically comes back with a value, we know we are in trouble. However, this is not super easy, because this is not actually static in terms of here is the value. Because to get this correct key, I would need to know what get bytes does. Only then I can reconstruct the actual byte array that is my key. I need support for things like fields in that case, because this is read out of the field here. And there are things going on like string concatenation. This URL is hard-coded. My analysis can give it to me. It's not a problem. However, to find the real URL, I have to support string concatenation. And this can get a lot more complex if, for example, someone would implement SHA-256 hash on his own, put some value that is in the code as a constant through this SHA implementation, and then concatenate it here for whatever reason. If I want the final value, I would be able to know what all of this is, and then say, this is the correct hash. So value analysis is far more than just grabbing for constants here. And we have seen this. I think this comes out of one of the Android apps we've analyzed. So people obfuscate their apps. They don't want you to know to which server they are connecting. So they do some mumbo jumbo here, which essentially is not real crypto, because everything is in the code. If you just look at the code hard enough, and maybe have a beer or two, you can reconstruct what this URL is. The question is, can your static analyzer do it? And for that, you need support for loops. Sorry, we don't know what a loop is, but you somehow need some definition of a loop and some analysis of something that you call a loop. And then you have to support for all these arrays, for calculations, and so on. Otherwise, you don't get a value. Now, if we want to know whether a value analyzer is good or not, we have to somehow have a benchmark. We need to have applications where we know what the outcome should be of the value analysis, and then we take a bunch of value analyzers, we run them, and see what their precision is, what their recall is. How many values do they find, which values do they miss, which values do they report that are just nonsensical. Now, the problem is that what I've presented you so far is actually a very particular instance of a value analysis problem. Take this code. There are many formulations of what a value analysis could give you here.
what we call a precise value analysis would just give you the 10 C's in a row. However, some other analyzers say, well, this is C repeated 10 times, you could say, as a regular expression, or C more than once, which is also somewhat capturing what is going on here, or C 0 or more times, which is also somewhat a representation of what we have seen. And for this example, this is pretty much equivalent aside from the length, but it really depends on your use case what you have. So when we're talking about concrete value analysis, and this is what the benchmark suite I'll present in a minute is about, we're talking about all the necessary informations in the program. So for example, if we did not know how often this loop runs here, then this would probably be the best thing we can do. We're not going to get there if we don't know how often we want to repeat C.
Sorry, can you use the mic?
Oh. Okay, no problem. Usually I roam around the place and just scream. Okay, then sorry for all the people on the internet. Concrete values. So, to get these, all of the necessary information must be in the program. The values must be deterministic, so if there is kind of a random number generator, then I cannot give you a value. I can only give you a formulation that says this part I don't know. There should be a small set of possible values, because if I want to enumerate all of them, and there are billions, I might be spending a bit longer than I expect. And a good example of this is obfuscated code, because there was an original value, people just don't want me to know it, so I can reconstruct it and get the original value back. There are other examples like regular expressions where people say, I can tell you what this program formulates as a value, but it's not like one value. It's, I know that this is repeated maybe depending on user input between 5 and 10 times. Totally fine. It can also over-approximate the language. It can deal with parts that we don't know. Then you just have, foo, or you know it starts with F and then there are some O's, and that's it. Or even the last one, it's a perfectly fine representation of the value. It's also a perfectly useless representation of the value. And then there is range analysis that people also use, where they say, okay, we're talking about an array or maybe memory. I know where it starts, I know where it ends, or I know where it starts and how long it is. This is also what you could ask a value analysis. Then you don't want the contents of the memory, you just want to know the ranges. And in this work, what we're talking about is concrete values. We know that there are use cases for the other ones, and there are cases where the other ones are actually better. But mostly for security properties, you're talking about, in Android apps for example, which URL are we connecting to? Do we have a hard-coded key? Do we have hard-coded credentials? What is the block cipher mode that is being used here? And all of that is concrete values. So, now I said if we want to have a value analysis and want to benchmark it, we need a ground truth. There is already an existing tool called JSA and it has a benchmark suite. However, it's far from perfect, because for this code they say we have 3 regular expressions. If your tool is great, it will give you C 0 or more times or null. If it's less good, it will give you C 0 or more times or null. And if your analysis is crappy, it will still give you get the point. So neither of these representations is super precise. So this is not what we want in a test suite. Plus, we know that this is never going to be null. Why on earth is it in there? Which means, when we started this work, all we wanted to do is look at the state of the art of value analyzers. And we were disappointed with JSA, and then we said, let's do our own benchmark suite. There must be something better. Because you can get as concrete as you want with your value analysis that you came up with. You might even get a Turing Award-winning value analysis, but in JSA, you get the same score as someone who just says, come on, this is C, like 0 times or whatever. So, what do we want? We want a ground truth with exact values. And we want them to be correct. So ideally, we want the ground truth to be generated automatically from what will actually be computed at runtime. Or else some dude will just write some garbage down and we have to deal with it. we want support for Android and Java because this is what we were interested in back then. And the test suite should contain common challenges. So if somebody has a good handling for loops or for arrays or interprocedural analysis, this should show in the benchmark suite. He should have a higher score than someone who just looks at straight line code without anything. And then we want statistics. If we say you're better in the benchmark suite than that other guy over there, we want to know, why does this happen? Do you have a better support for loops? Do you have a better support for interprocedural analysis? Because only then we can learn from it. So this is what we built out of this. We generated a bunch of test cases in Java code. These test cases are then compiled. And now two things happen. So firstly, we run these on the ground truth analyzer. So if it's Java code, it will be run on the JVM. If it's Android code, it will be packaged into an Android app and will be run on an emulator or a phone. And once this has run, you know the value that this test case computes. And this will automatically be annotated to the test case and will become metadata of the test case. You never specify the ground truth, you just write the test case. Plus, as I said, we wanted to know what this is about. Is this a challenge for loop handling or not? Or is this for interprocedural analysis? So the challenge analyzer will make these sort of statistics and will also put it to the metadata. Now that we have our annotated test case, we can run the different value analysis approaches. So if it's for Java, we put it into a jar and feed it to the value analysis approach. If it's an Android test case, we put it to an APK, run it through the value analysis approaches. The evaluator then just compares the results that every approach has produced with the metadata. And then you know, okay, JSA or Blue Seal or Stringhound or whatever they are good on this and bad on this. And you have a couple of challenges there. For example, the correct handling of fields. We have seen this in the previous talks. If you mess up your fields, you might actually have false positives due to cross-referencing. Or, for example, what about the typical obfuscation style analyses? You have arrays, you have arithmetic calculations, you have loops, you have API calls like arrays to string. If you don't have a model for arrays to string, you will not get a value out of this one. And I'm not going through all of the test cases. There are very many that we have in the test suite, and we of course make this publicly available. It is already on GitHub. So when we compare this to test suites that already exist, for example, we find out that we have quite a different distribution of what the challenges are. So for example, to succeed in our test suite, you have to have at least a quite good support of string builder and string buffer, because we've seen that this is what is often required, for example, when handling obfuscation in Android apps. You have to have a good grasp of interprocedural analysis and arithmetic calculations. And now we ran a number of analyzers on that. So the interesting thing is that the scanners where we put an asterisk, they report exact values, the other one report regular expressions. We match regular expressions against precise values by saying if the precise value is in the language of the regular expression, well, okay. We have some special casing. If you just put dot star, we say you didn't find a value, because that would be highly unfair. And what you find here is that many of the approaches actually are quite lacking. So Valdroid is pretty good, Stringhound is pretty good, Harvester is somewhat good. Harvester is a dynamic or hybrid approach that does slicing and then generates a new APK and executes that APK on the phone. Problem is, if something inside that APK crashes because the slice was not an executable slice, you're in trouble, you don't get a value. Or you get a partial value because someone catches the exception and the program continues. So actually this performed on JVM test cases worse than on Android test cases, because the original publication was on Android, but here it was kind of lacking. Stringhound, the paper reports on Android, but the problem is that they don't have the models for executing on Android. So you can actually just run it on the JVM, but not on the actual Android phone, which makes the comparison a bit harder. But nevertheless, you see that there is still a lot of room for improvement in value analysis approaches. And if you just try the old JSA test suite, then you will find that, this is a solved problem. It isn't. This is just because of the crappy kind of ground truth that you see in JSA. Just very quickly, a couple of interesting results. So why should I care about this? This is not complex code. You have a string, a prefix, then you append numbers to it, and then you append after loop. And when you look at the results produced by some value analysis approaches, you will find correct values, but also things such as null, comma, start. Why? Or JSA says, well, I have a regular expression. This is an approximation. It's start and something. Start.something is not helpful. Then, in another test case, for example, JSA then again gives us a regular expression that is just super over-approximating and not really helpful. Here you have a value that you can either get right or wrong. JSA says, well, you might be right or you might be wrong. Yeah, thanks a bunch, JSA. BlueSeal even says, okay, I concatenate the two. So these approaches, even while this code may sound trivial or look trivial, these are still challenges for many value analysis approaches. As I said, we make this data publicly available. Valbench is on the internet. If you have your own like super secret patented, well no, if it's patented it's not secret anymore. Anyway, if you have your own value analysis you want to test on this, feel free, report the results. Maybe we can also put a list of current value analysis approaches and how they perform. That would be very interesting. The replication package contains all the generators as well. You can also add new test cases if you want. And this is just a call to have a better evaluation on these tools, because the original papers, they of course said our analysis is great. They didn't say we report a bunch of garbage. At least the sentence was in none of those papers. So thank you very much for your attention, and I'm happy to take questions.
Thank you very much. Now, where are the questions?
So maybe coming back to your evaluation slide where you had all of those different... yeah.
This one.
Yes, exactly. So I was wondering, because you said those with an asterisk are actually those that have regular expressions, and it's striking
No,
that
other way around. Those with the asterisks produce exact values. JSA, for example, produces... those with asterisks are exact values. JSA, which doesn't have an asterisk, is one of the core regular expression-based ones.
Oh, that's interesting. Okay, because I was first thinking that the regular expressions save them, but apparently it's the other way around.
No, the problem with the regular expressions is twofold. So, firstly, you can get a useless but correct regular expression like dot star, which is correct but doesn't help anyone. And the second thing is it hides that tools are often unsure by just putting, it could be the right or the wrong or something totally else. This is what you get here. It says null or right or wrong. The right one is in there, but there's also a lot of garbage.
Mm-hmm. Okay, thanks.
So perhaps one more question. You use arrays here. Are these arrays which you take into account always of constant size? Or could there be obfuscation also in that you kind of make these numbers somehow weird?
This is something I would need to look into the data set. So in general, this depends on what your analysis tool can do. For example, Harvester is based on backward slicing and execution. So even if your array size is not constant, that should work out in theory with all the problems of making a slice executable. Veldroid is an approach that slices back and then simulates the code, very much like abstract interpretation. Should work. Stringhout does a cross-compilation from Android to Java and then a simulation. Should work. For JSA, I'm very skeptical.
Okay, thank you very much. More questions, please. So I think everybody's exhausted or happy or both.
Asleep.
So thank you again.
Thank you.
Then this finishes the suite of presentations, but I hand over now to Raphael and Cindy for last activity. But before that, let's thank them for their nicely organized program and the work they have invested to let this be.
Thank you for staying until the end. I think we've had really interesting talks, both from the papers and the keynotes. We wanted to thank the members of the program committee who've been doing all the hard work before we got there. So here are all 11 members from the program committee. They're also on the website. We also wanted to thank Luca and Helmut, who kindly agreed to do some session sharing, mostly at the last minute. So thank you, Luca, who's hiding somewhere in the back, and Helmut, you've just seen. And then we wanted to give a Best Presentation Award. So this is like a usual award we give at SOAP. The prize of the Best Presentation Award is hidden in the name of the workshop. It's been really difficult to decide because we've had really interesting talks today. And in the end, we decided to award the Best Presentation to Giovanna for her talk on the better approximation of interleaved disk reachability. So Giovanna, congratulations. I need to fetch the soaps.
Just give us 1 second to get the gift, the prize.
Does it just mean I smell bad?
And so here are the famous soaps from SOAP.
Thank you so much.
They're made locally, but from where I live, so not that locally. And really, congratulations for the really nice talk.
Thank you.
And then, yeah, we have one last thing, which is there is a welcome reception this evening. So this is a PLDI-wide event, but it's open to everyone who has one of those. So basically everyone, I think. Recommended departure is in 30 minutes from here, and you'll have more information on the PLDI website. Did I miss anything? No. Okay. So with that, we're good, and we're closing SOAP for this year. Thank you again for being here, interacting, and well, we hope to continue the discussion here, maybe at the reception or during the week. Thank you all.